I've always believed there had to be a better way to move an object from point A to point B. There just had to be. So I spent 2 decades looking at hidden momentum.
You do think you've discovered a propulsion mechanism that could get us interstellar travel.
I take those lifters and I put them in a plastic box and put it on a scale. You turn it on, the thing lifts up, and the weight flatlines, does not move at all.
Still about 200 micronewtons of force still inside.
How many variations of this experiment do you think you've tried?
We are close to 2,000.
2,000 instances of the experiment, or
no,
2,000?
2,000 variations.
Holy shit.
2 test articles. Each one's tested multiple times.
If you were to apply that to like a satellite in space in a zero-gravity environment,
it would accelerate with the power off. Can't explain that to the scientific community. I just can't.
The idea that you could just charge it up and leave it there and it gets thrust, like, it hurts my brain to even imagine how is that possible.
These are very weird things.
It's like you create this thrust mode that just keeps going.
I don't think I'm bending space-time. Maybe I am.
For over a century, humanity's journey to the stars has been held hostage by a simple, unyielding truth. Newton's third law. For every action, there's an equal and opposite reaction. It's the law that powers every rocket, every satellite, every probe we've ever launched. And it's also the law that keeps us trapped here on Earth. In order to get to the closest habitable planet in our very own Milky Way galaxy, a place called Proxima Centauri b, it would take you 50 to 80,000 years in a chemical combustion rocket. You would die before even getting 1% of the way there. And if you somehow figured out a way to live for thousands of years, by the time you came back to Earth after a trip like that, it would be totally unrecognizable. You'd be playing out the ending of the Planet of the Apes. To go anywhere in space, you have to carry fuel, massive amounts of it. Over 90% of any rocket's mass at launch is just propellant, pure fuel, burned and ejected out of the back to push the remaining 10% forward. Launching a rocket to get a satellite into space is like flying a fully loaded 747 to deliver a suitcase.
One of the challenges we have to solve is orbital refilling, where we dock on orbit and transfer propellant.
The modern king of rocketry, and Mr. Occupy Mars himself, Elon Musk, has publicly stated that Newton's laws are the end-all be-all for space travel. For some reason, he's quite adamant about that.
There's no way around Newton's third law, really. You basically have to expel mass.
The original godfather of American rocketry, Jack Parsons, believed this as well. In 1936, he and some colleagues at Caltech began launching the first rocket tests in western Pasadena. But what most people don't know is that a decade before Jack Parsons, in the 1920s, there was someone else at Caltech with some very different ideas for deep space travel.
Townsend Brown.
Townsend Brown.
Townsend Brown.
Townsend Brown. There's a guy named Townsend Brown.
Okay, Townsend Brown.
Brown had stumbled onto something that mainstream science still refuses to acknowledge. A possible break in Newton's laws, a new force, or perhaps a way to manipulate gravity itself with electromagnetism. Unifying these two fundamental forces has been the holy grail of physics for the last century, what Einstein died searching for. Townsend Brown discovered that when you apply a high voltage to certain asymmetric capacitors, they produce thrust. No fuel, no exhaust, no propellant, just electricity, converted directly into motion. A new model for space propulsion that could eliminate crude chemical combustion forever. Brown called his anti-gravity work electrogravitics. Meanwhile, physics textbooks called it impossible. And because of that, he was dismissed, ridiculed, and eventually erased from the official story of physics. But if you dig a bit deeper and read his incredible biography by Paul Schatzkin, you start to piece together a very different picture, one in which Townsend Brown isn't easily dismissed as an amateur quack. In fact, his work was witnessed by the highest levels of government and military.
Now we're getting some interesting territory.
People like notorious Air Force Chief of Staff Curtis LeMay, who courted Brown constantly. People like Edward Teller, the father of the hydrogen bomb. Bill Lear, the founder of the first private jet, and Agnew Bonson, founder of the Institute of Field Physics at North Carolina, a lieutenant colonel from Wright Airfield who went on to become a general named Victor Bertrandius, witnessed Brown's gravitator experiments in Los Angeles in 1952. He was quoted as saying, "Believe it or not, I think I just saw a flying saucer, and it frightened me." And if that's not all, we have audio of a deathbed confession from French aerospace executive Jacques Cornillon, who witnessed Brown's successful experiments in a vacuum chamber in 1956 in Paris, explicitly stating he witnessed a positive result.
So that was a positive result.
This is to go along with an 120-page report around that specific experiment that's widely available online today. Nonetheless, stigma, tech protection, and scientific suppression are all very real. Brown's work is still likely classified by the Navy to this day. Over the last 70 years, Brown's experiments never went away. They just went underground. They've been replicated all over the world in places as far as Japan, but usually by persistent hobbyist teams or aerospace engineers stringing some funds together and operating out of pure passion. But in deep black American aerospace, I believe Brown's work still exists in the form of whispers and vital subcompartments where it gets explored further. Okay, so that's the backdrop. Newton has us stuck on Earth, industry titans like Elon can't be bothered to explore new propulsion modalities, and Townsend Brown is a total ghost relegated to quacky UFO circles. That is, until today. Inside a quiet lab in Florida, NASA's lead electrostatics scientist, a man named Dr. Charles Buhler, has been running the same gravity-altering tests as Thomas Townsend Brown.
When we see about 0.1 grams, that corresponds to about 1 millinewton of thrust.
Only this time with modern instruments, more rigorous controls, and decades of electrostatics expertise from his work at Kennedy Space Center behind him. And what he's measuring is thrust. Real, repeatable, directional thrust. No combustion, no reaction mass, the future of space travel.
We say we have an energy crisis. Oh my God, the energy crisis. Well, it could be considered an energy crisis, but it's really a force crisis. It's a transportation crisis. How do you get an object from here to here?
At his company, Exodus Propulsion Technologies, Buhler isn't just replicating Townsend Brown's work. He's validating it, scaling it, showing literal weight loss on scales due to upward thrust. Again, Buhler is not some mid-level guy at NASA. He's the lead electrostatic scientist in the entire agency. And you're also, I believe, about to be the president of the Electrostatics Society, too?
That's correct.
And he's contributed two fundamental principles to the field of electrostatics that are now widely accepted. The question is no longer whether the Byfield Brown effect is real or not. The question is, where could this lead humanity? How can we scale this up? And what is the theoretical physics behind it? On this last question, Charles goes deeper on this show than he has in any other interview on his own quantum electrodynamics-based theory around how this force works. And I brought in my friend, a brilliant MIT-trained physicist named David Chester, to help stress test and sharpen Buhler's theory. What happens when propulsion no longer requires fuel? When the tyranny of rocket equations finally breaks? Without further ado, please welcome this week's amazing American Alchemist, NASA and Exodus Propulsion's very own, Dr. Charles Buhler.
Ignition sequence start. How is this possible?
Nothing too unusual about that.
Their existence cannot longer be denied.
Before we continue, I want to take a second to thank one of my favorite products in the world, KetoneIQ, for sponsoring today's episode. KetoneIQ is one of the very few things I use that gives me clean, sustainable energy without the crash. It's just this little shot, and I take a drink, and I feel like I'm on fire. No ups, no downs, no nervous system weirdness. Just clean, clear mental energy. The reason it works is pretty simple. It gives your brains ketones, which are our Almost by definition, its most efficient fuel source. Instead of pushing your system, it actually feeds it. In fact, your body endogenously produces ketones. So when you drink this, it supports deep focus, long conversations, and sustained mental performance. It was originally developed through a multi-million-dollar military program designed for high-stress environments where cognitive performance really matters. And today, it's used by founders, researchers, podcasters like myself, and people who need their mind to work when it counts. I always take a sip of one of these things before long podcasts. This product is also really personal for me because I've known the founders, Jeff and Michael, for over a decade. These guys are awesome, and for as long as I've known them, they've tried every supplement, biohack, and nootropic under the sun. So it was a pretty good signal to me that they decided to start a company around ketones. I use KetoneIQ regularly. It's like a mental cheat code, and it's genuinely one of the cleanest energy sources I've ever found. So before we get back into the episode, please visit ketone.com/alchemy for 30% off your subscription order, plus receive a free gift with your second shipment. Again, that's ketone.com/alchemy for 30% off your order. Or you can find KetoneIQ at Target stores nationwide and get your first shot free. Seriously, this stuff works. Thanks so much to KetoneIQ for sponsoring today's episode. Everyone talks about the Bermuda Triangle, but no one warns you about its colder, weirder cousin. In the heart of Alaska lies the Alaska Triangle, where planes disappear, hikers vanish, and the only thing that shows up reliably is my Wild Alaskan Company seafood box. I'm being serious here, guys. I definitely don't trust flying over portals, but I do trust this fish. Most seafood, I can't even look at it without wondering if it was farmed in a glowing vat near a nuclear power plant. But this fish, 100% wild caught, flash frozen off the boat, delivered straight to my door like it teleported through one of Eric Davis's wormholes, and it still tastes better than just about anything your cousin microwaves. No antibiotics, no additives, no fish farm sludge, just real fish. Coho salmon, Pacific halibut, and my favorite, the sockeye salmon. Not all fish are the same. Get seafood you can trust. Go to wildalaskan.com/Jesse for $35 off your first box of premium wild-caught seafood. That's wildalaskan.com/Jesse for $35 off your first order. Thank you so much to Wild Alaskan Company for sponsoring this episode. I'm here with Charles Buhler, who, this is a holy grail interview for me. I'm like a kid on Christmas because it's been like the search for Buhler ever since, we connected a couple years ago because I made this Townsend Brown documentary. And as you know, and my audience knows, I'm obsessed with this mid-century inventor, Thomas Townsend Brown. I think he found a real force that lies outside of either the four fundamental forces, might have merged gravity and electromagnetism, I don't quite know, but something that transcends kind of our chemical combustion modalities that will take us interstellar. And as soon as I came out with that, a bunch of people hit me up and they're like, you got to talk to Charles Buhler. He's the lead electrostatics scientist at NASA, and he's been doing this experiment, but his own kind of version of it, his updated, better version of it, in a vacuum chamber he's had access to for a decade plus. And so we connected a little bit. We kind of fell off. I'm so grateful to have you here now. It's just a total honor. And you're also, I believe, about to be the president of the Electrostatics Society too.
That's correct.
So you have the credentials to say, if you're saying that we found another force, you have as good of credentials as anybody. Is that right? I mean, don't be humble.
To say, but, I think I know enough about electrostatics to say that, but we're always still learning.
What's your current job title?
So I am the lead scientist of NASA's Electrostatics and Surface Physics Laboratory, part of SwampWorks at Kennedy Space Center. So before I go on, I have to diverse to make everyone aware that this is not affiliated with NASA. Any of this work that we're doing.
Absolutely.
It's not sanctioned by NASA, and we are not given any credence to NASA in this.
Disclaimer accepted. I think maybe it's a little bizarre that NASA wouldn't want to immediately kind of jump on this work. Okay.
But they're probably going to be a customer later on. They're not, we're not working this technology at NASA. At least not in my laboratory, we're not.
But is it safe to say you're the lead electrostatics scientist at all of NASA?
I would say that. I mean, we only have one electrostatics lab in all of NASA, and I lead it. So,
And you
yes.
run it.
So by default, yes.
Yeah. Okay. So again, if this sort of force were attributable to basic electrostatics, you would know.
Sure.
Let's back up a second, and that's a really impressive, cool title. What does somebody who leads electrostatics at NASA do?
Our lab does a lot of things. It was founded about 26 years ago by Dr. Carlos Galle, a physicist who spent a summer working at Kennedy Space Center, came back the following year and started the lab. We do electrostatics at NASA at Kennedy Space Center because of incidents that occurred in the 1960s. So there was an incident that trapped 11 people in a spin test facility where they accidentally set off a rocket, a solid rocket, and there were some casualties there. So we also had the Apollo fire that you've heard about. So we've lost, I think, 14 people to electrostatics at NASA. So Kennedy Space Center has kind of led this effort to study this phenomena and test it. And a lot of the tests that we've been doing date to the 1960s, long before they had standardized testing from electrostatics. So Dr. Carlos Galle formed a research arm of that test about 26 years ago. And
aren't there also issues with lunar dust, getting attracted to the lunar lander, and electrostatics sort of allowing or removing the dust or something like that? Is that a thing?
Yes. So when I get on the stand and I talk about these things, my pedestal, I always talk about the safety and need to study electrostatics, but no one pays us to study electrostatics. It's a case-by-case thing where people will give us funding to look at and investigate, just like any other investigation. But it doesn't pay doesn't pay the bills. So what we've done is we've understood some of the needs for NASA that are in the electrostatics realm. For example, the dust mitigation aspect. So dust is considered one of the two greatest challenges that have to be overcome for long-term human presence on the moon or Mars. The dust was very problematic for the Apollo astronauts, where they couldn't even do a fourth EVA. They could do 3, they couldn't do 4. Dust would clog the suits and get into the arms, into the helmet, into the joints, and it just prevented further EVAs, extra vehicle activities. So the dust mitigation is a serious one. It's taken by NASA. I think every center is working on it. But we actually have many dust mitigation technologies that we've developed over the years. Our primary one is the electrodynamic dust shield, the EDS. So this uses a surface that has embedded electrodes inside of it that lifts and removes dust without moving parts or gases or fluids or anything.
Wow.
So we can embed that into glass. We can embed that into thermal radiators, solar panels, solar arrays, all kinds of materials.
Very cool. And wasn't there recently like a lunar dust mission?
That's right. So we were almost just over a year ago, we landed our EDS payload. It had 9 EDSs on there. So there were 6 EDSs used to get dust onto us, so we can use our EDS to show that we can get it off.
Cool.
So we tested a thermal radiator EDS. We tested a glass EDS on the moon and a camera EDS. So we tested the technology on the lunar surface successfully.
Very
exciting.
Cool. That's amazing.
So you work 25 years on something, you finally get it to the moon, and it works. You're pretty happy.
Congratulations. Yeah, it would suck if it didn't. After 25 years,
Yeah.
It's a lot of sunk cost, a lot of time and effort and energy. One other very credibility enhancing thing about you that I think it's really important to note is you've contributed to the field of electrostatics outside of this anomalous force that you're talking about. Is that right?
That's right. So, I've been in electrostatics for 26 years, and it's been around obviously for a very long time, but it doesn't get the attention that the other scientific disciplines get. I don't feel it shouldn't be the case where I come in, as a young kid, and I should not be discovering phenomena in electrostatics, like I did with the showing that there's no brush discharges in high vacuum conditions. High vacuum conditions, I know obviously people don't have access to that, but it was not, generally accepted that this did not happen under vacuum, pulling off charges from an insulator. We know that happens very well in air. Why doesn't that happen in high vacuum, when we were able to show that you cannot get the burst discharges the way you do in vacuum as you do air. It's more of a gas breakdown effect, which could be, expected, but it was never shown. So it's a little bit surprising.
And you were the first person that showed that.
As far as I can tell, yeah. In the literature. So, and that's, obviously because I had interest to do that for the NASA mission. Not a lot of people want to do electrostatics in high vacuum, but it's something I love to do every day.
Clearly.
And the other phenomena that I discovered, which I thought would be child's play for sure, would be the fact that if you take a vat of particles of all the same size and tilt them, they would roll over top of each other. And the ones that do the rolling are positive, and the ones left behind are negative. This is very intriguing because for particle charging dynamics, we know that in volcanoes and wind cloud formation, the larger particles will become positive and the smaller ones will become negative. So there's a size difference. We don't exactly know why it occurs, but I was the first to show it has nothing to do with size. It has to do with dynamics. So the particles that partake in the interactions more often will become positive than the ones that do not. So if you have a cloud mixture of bigger particles, giant spheres with small particles, the bigger ones are getting bombarded a lot. So you'll have the ability to sample more than the smaller ones. The bigger ones will be positive and the smaller ones will be negative. There's some basic band theory reasons why that might happen, surface state theory, but no one's ever showed that.
What are the practical implications of both of those kind of more conventional contributions to electrostatics?
Probably maybe electrostatic beneficiation. That's where you separate materials. We do that a lot of times when we separate plastics. When you recycle them, you can chop them up and you can tell the high density from the low density polyethylene by tribocharging them together into fine particles, splitting them in a field. One goes one way, one goes the other. So you can separate plastics that way. There's a lot of different uses of tribocharged, electrostatically charged materials for industry. That's one case. Obviously explains lightning, cloud-to-ground lightning, volcanoes, and things like of that nature. So there's a lot of interest in our community on the triboelectrification of materials, especially for the Moon, Mars programs.
Because you're probably living, the dream of, many nerdy kids in their bedrooms right now, thinking about NASA and, working and, sort of cool physics and electrostatics, doing stuff for them. What's your journey there? How did you get hooked up with NASA? Yeah.
That's a long one.
Okay.
Well, essentially, I've always had a fascination with space as a kid. I've always have. And that didn't end when I went to graduate school and after I graduated. So, my PhD is in theoretical condensed matter physics. I got that at Florida State University while working at the National High Magnetic Field Lab. And after that, the grad students, we went different directions. Some stayed in academia, some went, got jobs, in industry or whatnot. And I decided to go to NASA. And there was an opening for a postdoc in the electrostatics lab under Dr. Carlos Calle. He's trying to start that laboratory back in Florida. I was living in Tennessee at the time. I said, it's a chance to get into NASA, see what it's about. What was there to learn on electrostatics? Everything's known. It's Maxwell's equations. There can't be anything to learn there. And when I got there, I realized that even the most fundamental studies in electrostatics were not complete. Even understanding how you rub two materials together and you separate them, one's plus, one's minus, how does that even happen? They didn't even know if it was the electrons responsible, ions, material transfer, all the above, none of the above. So there was a lot to learn. So I found it to be a very interesting field of physics that the mainstream community doesn't care too much about. So I found it as a nice way to learn and to learn something new. And that's what got me excited about electrostatics once I got there. And what really got me excited is it could help people. I could solve problems. That's what electrostatics does. It solves problems. And it's involved in just about every industry, whether it's making the dust masks for those are made by 3M, those N95 masks fighting COVID. Those are electric filters. So you actually make those using electrostatics. and they actually work for 8 or 9 hours because they can trap those nanometer particles. You don't know these things. Microphones are all electrostatics properties. That's an electret. So there's so many different fields that electrostatics dives into, and it was very useful for us to, as NASA, go to these electrostatics conferences where you have the pharmacy industry there, the biologists are there, chemists are there. It's a very wide, open discipline because they all need help in electrostatics, and they're all advancing that field. And so I could use what I learned there to apply to NASA. So whether it's the EDS technology that came from that community or other technologies that we learned from that community, like the electrostatic precipitation, that's air filtration. There's so many technologies that come out of that field. So it was originally discovered by, founded by the scientists at Xerox back in the 70s. So it has a very rich, deep history in America, in that North New York area with Cornell and, Corning, and Kodak, and these companies that are, very prominent back in the 60s and 70s formed together this electrostatic society, and they share that technology with people.
It's fascinating. Yeah, I always found it interesting that Townsend Brown, along with his thruster work, which, involved, what he thought would lead to interstellar travel, he also, I believe, was responsible for the patents that ended up, Sharper Image ended up buying them, and it was like an ion, air filter or something. And so I found that really fascinating. At what point did you get the idea that maybe there was another force here that could take us to the stars, and that chemical combustion and the rockets that you don't work maybe directly on, but you work, around with your work at Kennedy Space Center might not be, the frontier of space travel?
I always knew there was something else, something more than just Newton's laws. So I kind of tailored my career just to try and understand physics enough to see if something else could be done. Just anything. So this goes way back into high school. So I started doing tests in high school. I started doing tests in college. I built rigs in graduate school. So it never really ended. But so I continued to do it. But it's hard to say when did it start. I've always believed, it's just a belief, that there had to be a better way to move an object from point A to point B. There just had to be. Newton's laws is great. Relativity wasn't very useful to me, probably because I just didn't know it. But electricity and magnetism seem to have a nice appeal because, it's 19th century. There had to be a 19th century equivalent to it, to momentum conservation. It had to be. So I spent, 2 decades looking at the conversion from field momentum to mechanical momentum, if you're familiar with that field. So essentially, you can convert momentum stored in the field into real momentum. They've done that in the 70s with the angular momentum. But the linear analog to it was always hindered by a third momentum called hidden momentum. So I went out on a limb and tried to find systems that did not have hidden momentum.
Fascinating. Well, we're going to dive deep into that and your theories around it. But I think first, just, for the lay audience, mass ejection is the current kind of paradigm. And so it's Newton's third law, and it's just, you expel a ton of mass. A lot of these rockets, like look at SpaceX's, Starship, it's mostly fuel in the rocket itself. That's most of the tonnage is just fuel. And then you obviously have a decently high payload capacity on top of that, but that's a very small percentage of the overall rocket. And so it's very inefficient from that standpoint. And then because you have a limited amount of fuel, you can't really get to Proxima Centauri B. And if you could, it would take you 80,000 years with current speeds. And that's the closest habitable planet. So I always, bring these things up because even if Elon Musk were sitting in your chair, there's no argument he would have to defeat. That's just physics, there's nothing he could say to that. And so I think what you're looking into is the most, people can come back with first principles arguments and say you're wrong, but it's the most important thing.
For space, it absolutely is. There's no question. Because like you said, I think it's 95% of a rocket's mass is just fuel.
Yes.
And you expel it almost immediately and then you're done with it. So then you're just out using inertia to get you wherever you need to go, unless you have a little bit of fuel to get back. But, just the amount of fuel that's going to take to get to Mars, how many starships it's going to take that have to be fueled just to get to Mars. It's just astounding. It's an incredible amount of massive fuel.
Yeah. I mean, just to the moon. I don't know if you know this, but the Starship burns 9/10 of its fuel tank. It goes into low Earth orbit. Then it does butt-to-butt refueling with another Starship that goes up, burns 9/10 of its fuel tank, and then that gets disposed of. So you end up with 2/10. You have to do that 8 more times. Then you have, a full tank. And then that goes to the moon. And that's just the moon. That's not even Mars.
Oh, it's astounding, the numbers I've seen. And
it's astounding.
It doesn't seem rational.
It doesn't. And you never bet against Elon. He any engineering feat, people were saying Starship itself wouldn't work. And the Pez dispenser flap that allowed the Starlings to come out was like, would get ripped off, and that there are all these things they had. And it seems like it's starting to work. It has orbited Earth. And then there's still, modifications and updates they need to make. So, not pouring cold water on that engineering effort. But again, I do think from a physics perspective, from a pure design perspective, if there is this other force, we should obviously be looking into.
Sure. I mean, there's got to be a better way. And I always believed, ever since I've started studying science, that there has to be another way. So even as a young kid.
Totally.
It doesn't make sense.
Yeah, I agree.
It just doesn't make sense. So
Yeah.
it's like, so I kind of just tailored my career, just understanding science, what we knew about it, everything that I could.
So clearly you had this kind of imagination and just preconceived idea that maybe we could transcend the limits of chemical combustion. Maybe there was something sitting in electromagnetism, this 19th century modality. Describe, and hopefully in detail, kind of in visceral detail, the first time you witnessed this force and what it felt like.
I would say the first time I witnessed it, or a force, based on a theory that I had, was probably 2010.
It's wild.
So that was 2010 with my brother-in-law, future brother-in-law. We weren't married then, but he was in the laboratory working with me, and I set up an experiment, and I had him run it. Now, the other scientist I was working on another project, thought I was just full of BS, which is perfect, fine. So he did not help us at all. He's a seasoned physicist, very well known in his field, and just thought I was just doing garbage. And that's fine. I don't care. So I still had, my brother-in-law Nathan do the experiment in the laboratory, and we were looking at a laser on a wall, so you can see small displacements force in a chamber. It wasn't an air chamber, it wasn't a vacuum chamber. And he did the test, and we saw the laser move. I'm like, oh, well, that's pretty cool. It's supposed to do that, I thought. And my colleague, Dr. Clements, Sid, stopped what he was doing, went over to Nathan. Okay, you've done this. Okay, now we got to do that. He just completely immersed in that experiment after that.
Yeah, wow.
It was like, what is happening here? This is really crazy. Something is weird. So that was the first time. That was very, very exciting for me, because it's the first time we all seen it, and I happened to be a world-class scientist there to help us. It was actually like, wow, what happened here?
So you kind of
cool.
You converted him almost, at least into thinking it was worthy of inquiry.
I didn't need to say anything else after that.
Yeah, that's amazing. Is he now a believer in?
Oh, I think so. He's seen it a few times.
And what's his background?
He is an electrostatics expert.
Okay.
He is my mentor.
And what's his name?
Dr. Sid Clements.
Dr. Sid Clements. Okay. So
yeah, he is my mentor. So that's where I learned electrostatics.
That's wild. But he saw your experiment and he was like, oh my God, there's something else here.
There's something there. It's exciting. It was an exciting moment.
That's incredibly exciting. And so you see this, and what do you think is the next step at that point? Because, you see this little displacement, this laser displacement based on this possible force. Mm-hmm. Do you design a new experiment right after that?
We designed many experiments after that. It led us down many different paths. That's kind of how this goes. If you don't know exactly what's happening, it can lead you down different paths. Some were successful, some were moderately successful, some weren't. Really didn't hit too much success after that until I met Andrew. Okay. Here's the story with that, if you're interested.
I'm very.
So we had a colleague, Andrew and I, a friend named Mike. He knew about us working on this independently for years and never told us. Never did. He wanted to see if we can do it independently, like a race against I don't know who. But
So he was playing dumb.
he was playing dumb.
He knew about this force, and he was just like,
Well,
let's see how far they get.
He knew Andrew was working on it. He knew I was working on it. He just wanted to see who would win the race.
Oh, Jesus. That's this Machiavellian level,
It's like
4D chess going on.
So, and Mike, his excitement was that, how we were both working at NASA or as contractors or been at NASA. And he was just super excited that we were not doing this at NASA. It's like, this has a chance. Because once you get at NASA and get in bureaucracy and get in the government, there's a lot of ways that can be hindered. So he was loving that we decided to do that outside of work. Of course, at the time I wasn't working at NASA. I was a consultant for ExxonMobil. But so we worked together because Andrew needed an electrostatics guy. Andrew knew he was getting into the realm of electrostatics. So
what was Andrew's background?
Andrew?
Yeah.
Andrew Arajima, he is an engineer.
Okay.
He's been an engineer for, 35 years or so.
And he goes by
years.
Drew.
Drew.
And he wasn't getting into this via electrostatics. If that's the case, what exactly was he doing?
Well, he was using the term electrogravitics.
Oh, interesting. So this is the Thomas Townsend Brown
So
lineage.
He's in that. It was in that camp.
I love it. I'm in that camp.
I'm not exactly there, but
Yeah.
I might move there. We'll see. I don't know. I'm still on the fence on the gravitics part.
We'll meet in the middle. We'll figure it out.
Yeah. To me, it was a little bit pretentious. It's like, okay, you're doing gravity and with electromagnetism? Maybe.
So you meet Drew, and then what happens?
So at the time, I was working with the field momentum converting into linear momentum stuff. I wasn't in the gravity world. I was in the field momentum world. So we go to Drew's house. I take my wife, and we spent 4 or 5 hours looking at his setup, looking what he's doing, and I gave him a lot of pointers. You could try this, try that, try this. All the things I would do in electrostatics to help him along. His experiment looked very different than mine. His was just a needle, high voltage needle in a Teflon casing. I said, it's pretty interesting. If he's getting forces with that, that's kind of interesting. I don't know how you would. Until my wife told me as we're leaving the driveway. My wife was like, isn't that the same force you're working on, just manifested differently? She's a physicist too. She's the best.
Wow.
So we go back and forth on these things.
Is she at NASA as well?
She is.
Wow. What does she do there?
She's in the launch services program.
Cool.
So she doesn't have her PhD in physics, but she's taken engineering physics in undergrad, and she's really good at math. So if I need help with math, I give, hey, Janessa, help me with this equation. Help me with this integral. She'll have like a baby on her arm. Okay, fine. You can't do it. I'll do it for you.
That's awesome.
She'll come in and look at the whiteboard. She's like, this is not right. So she's very smart. It's fun to bounce stuff off her. But she was clear. She's like, no, you should look at this, your force that you're trying to do with his setup, see if you're working on the same thing, just a different twist. I said, well, that can't be right. So I went back to my lab and I made a needle, but I did it differently using what I thought would work. And I put there's videos of this on our website. You put a tube over the end of the needle and you put Scotch tape on the tube. So there's no ion wind getting out. And you shove the needle in that tube. You encase the darn tube. Then I cranked up my power supply and that thing moved 3-4 feet in the air. And I sent that video to Drew. And Drew was like, oh, I guess we're working together now.
Wow. So you have achieved how much force roughly now with your current experiments?
Additive, somewhere to 5 to 10 millinewton range.
Okay. And so for people listening, if you were to apply that to like a satellite in space in a microgravity or zero gravity environment, that would be huge.
Sure.
You would be able to do...
Yeah, initial markets. That's what we're comfortable with. We're a space company. We all work at the space agency, different levels, not just NASA, but the peripherals, and this is where we're comfortable with. There's definitely when we say when do we hit unity? Well, we've hit unity for space, unity for Moon, Mars, all of these places. So we can make flying cars on the Moon and Mars and all of that. So it's a very exciting place to be right now.
Yep.
Without any significantly huge development.
It could theoretically lead to deep space exploration.
Sure.
You could help maintain orbits for satellites where there's orbital decay.
That's what our hope is. Sure.
Okay. And you can move these satellites maybe to other orbits as well. Like there's a company called Impulse Space. They're like, they do like kick stages where you would move, between orbits, where maybe you'd go up on SpaceX rideshare with another group of satellites, but you'd want to move into a dedicated orbit. You could use a thruster like this to do something like that.
No doubt. That's what our goal is.
Super cool. And then what about like replacing rockets? Could we ever do that with this?
Well, if we get Earth unity, we won't need rockets, right?
That's true.
You have to think about things a little differently.
But could the 10 millinewtons of thrust turn into newtons of thrust? And could we end up launching things into space with this, Exodus method or this other force?
Our main goal, to try to do that. That's where the self-launcher is what we call it.
Do you have blueprints around this self-launcher? Do you have a sense of the energy requirements or anything like that? Or
we don't.
Okay.
But we're on the path. So we know what we need to do. We just have to go set out and do it.
Have you gone up over the 2,000 iterations? Have you gone up in millinewtons of thrust?
Sure.
Okay. So you have a sense of the levers to get more thrust.
There are levers, and there are several.
Uh-huh.
And we're trying to optimize those.
And what are the primary levers?
There's, like we talked about, voltage, the materials properties, the breakdown strength of materials, the type of signals we send, the physical limits on the materials. There's so many.
What are the ideal materials for this sort of experiment?
Well, we're dealing with high voltage, so we need materials with high dielectric breakdown strength, but we also have permittivity issues we have to contend with, geometry issues we have to contend with, static dissipation issues we have to contend with. There are a lot of other issues, and that's just the DC. When you get to other frequencies, or you get to other exotic types, charge injection, electrets, things can get even wackier.
Yeah.
So we are looking at some of the interesting materials now that have other properties, which I'm going to keep to ourselves for now, but it's something that's very, very interesting for now, just to see if it goes anywhere. It could lead to nowhere.
Yeah.
But we're just looking at it.
Cool.
There's other things out there.
In the Townsend Brown context, barium titanate and bismuth often come up. Are either of those relevant to your experience as well?
We have some experiments with barium titanate a couple of years ago. It's
Okay.
a good high permittivity powder. I don't know what the results of those were. They weren't particularly interesting. What was the other one you said?
Bismuth.
Oh, bismuth. Yeah, I've seen bismuth a lot. Bismuth looks like fun. I would love to test with some bismuth. There's some cool things that they found, the arts parts materials.
Yep.
Which is kind of neat because they had some weird geometries in there, which I would project that we would have needed. But to see that in real life already made, I was like, oh, that's kind of cool. I can't wait to go test those exotics, but that's down the road for us.
Yep.
We're going to try to stay focused and do what we're good at right now, and then work on the more exotic stuff later, I think.
And so in doing these experiments, did you have access to a vacuum chamber? Because I feel like it's been a lot of the reason, everybody always questions me on this. They're like, this experiment sounds very simple, because I always bring up the Townsend Brown experiment. And they're like, why has nobody done it yet? And I give two reasons. I say people always try to explain it away via the ion wind. And it's so similar to the ion wind related experiments that it's easy to do that. It's always easy to say there's ambient ionization in the vacuum. That's number one. And then number two, access to an industrial grade vacuum chamber is pretty limited, and it's obviously very expensive. And so did you have access, based on your kind of NASA background?
Yes. Drew and I have access to a chamber. He's got one at his house. He's very resourceful.
Amazing.
He funded it himself. It's a nice size vacuum chamber. He also has a second one that he's going to get online soon, which is almost a walk-in size vacuum chamber. So very pricey, but hopefully with some funding, we can get that thing up to par and running. But yes, we do have access to a high vacuum chamber. That's where we do most of our tests.
And let's describe to the audience why it's important that ion wind can't get out. Because this is how, I learned about all this stuff through Thomas Townsend Brown. And he used to do these experiments. So Thomas Townsend Brown's this super interesting, mysterious guy who pops up at extremely high levels of aerospace. He was at the Navy for a very long time. He was at Martin Corporation the year that Skunk Works was formed in 1942 or 3. There's an FBI document that is circulated now and out about him and says that he's the lead radar scientist in the entire Navy. He knows more about radar than anybody in the Navy. We have a lot of evidence that his electrohydrodynamics work, this electric fields to manipulate airflow work, ended up in the B-2 stealth bomber. So you have like 2 out of 3 things that he's talking about definitely being legit. And then the third thing he's saying is, I've merged electromagnetism and gravity. And he talks about electrogravitics. And it's specifically 2 experiments, 1956 in Paris, of which we have a witness who, there's an audio recording of a deathbed confession in 2009. This guy, Jacques Cornion, who's a technical consultant for Sud-West, which is, an aerospace corporation there. And, they say there is a force that is not only measurable in a vacuum at 10 to the -6 torr, but the force exceeds what you would ever see outside of a vacuum. And then he does the same experiment at the Bonson Labs at the Institute of Field Physics in North Carolina. And it's this remarkable thing where you have this guy, 2 out of the 3 things he's saying, probably right. You have, he's dealing with Curtis LeMay and the Rand Corporation, all these super high up people. And then this electrogravitics thing just gets stigmatized and people just kind of forget about it. And it almost feels like he has this wounded prairie chicken routine where he's trying to stigmatize his own work. And so it's fascinating. And the reason, this is very long-winded, but you mentioned ion wind. The way people write off any of these experiments, including Thomas Townsend Brown's, is they say that these capacitor experiments, especially if they take place not in a vacuum, you end up with ionized air. The ionized air then bounces off of other air particles, and it's basically just Newton's law taking place, and then you get thrust. And so that's very different than showing this in a vacuum chamber, or in this case, you mitigated ions in another way. Is that right?
Well, you kind of have to.
Yeah.
Otherwise, you'll see the ion wind thrust. So you can either cap it, enclose it in a volume, whatever you have to do. But you don't want the ion wind to be playing a role here.
Yep.
And one of the things that's different about the force that we're talking about in the ion wind force, at least in terms of geometry, is that the devices will move with the wind. So imagine a rocket moving in the direction that the exhaust is.
That's crazy.
So you have to remove the ion wind because of the stigma from it.
Yeah.
Because a lot of scientists have tried to do these things and they've seen the ion wind, and it's not a real force in the sense. It's not a propellantless force. There's propellant there, the wind.
Yep.
But the other thing is not. That's a different thing.
Yeah.
That's a completely different beast.
And you would be an authority in your ability to delineate between.
Sure. I do videos where I take those the lifters and I put them in a plastic box and I put it on a scale.
Yeah.
And you watch the weight. And you turn it on, the thing lifts up and the weight flatlines, does not move at all.
Wow.
So Drew was like, man, I've never seen that video before. That's conservation of momentum right there. That's what ion wind is doing.
Yep. So that's exactly like you have all these DIY videos of these balsa wood lifters with tinfoil, and you have the ions moving around the copper coil or whatever, and then you end up with thrust. But that is not this electrogravitic force, or what you were calling, this exodus force, or electrostatic variation force, whatever it is. That is different. That is another force. So it's important for any experimental physicists who want to pour cold water on this. And the funny thing is, Brown himself would use the electrohydrodynamic stuff, the stuff involving ion wind, to cover for the electrogravitics. He would literally because it's 95% similar,
Yep.
but it's not the same thing. And again, you are in a kind of an authoritative position in order to, you have the ability to delineate between those two things.
Yeah, that's important.
It is really important. Yeah. And it's important because it's always the first order debunk on this entire thing.
Sure.
So you do this experiment that eliminates or controls for ion wind. I'm assuming you, since then, have done a series of experiments to control for all sorts of other possible confounding variables.
Yes. So after Drew and I did these experiments in 2016, I think we spent about 2 years trying to package it. Now, there's one thing to put 100,000 volts on a device and have it move around in the room. Drew and I both knew that was completely impractical. You can't do anything with that because you have to make something to attach it to a vehicle, to a rocket, to something that people have to be around. And this better damn well go inside of a grounded box. So we made a lot of effort. It took a lot of effort those 2 years to get this sucker packaged up in a way so it can actually be transportable and confined. So that was the initial pull to go into to get into a system where we can actually enclose everything. Coulomb forces are the biggest killer in vacuum or in air. So you can apply high voltage to something, it'll attract to the wall, the floors, ceilings far away. It can still do that. So you have to make sure that everything you do is inside a very well-grounded Faraday cage. So that is another one of our our tests, our checks and balances. Do we have it inside of a Faraday cage? Is it all completely housed? Is it fields trapped within the system? Do we spin it the other way? There's a lot of checks and balances that we have to do along the way.
So Faraday cage would eliminate magnetic field interference?
No.
Okay.
Only electric field.
Only electric field interference. And then you also need vacuum chamber because, is that right or no?
You don't need it. It's a lot easier.
Okay.
Because you get rid of the air. The gas breaks down like 1 million volts per meter fields. So the gases start breaking down. And when they break down, they create their own charges. And when they create their own charges, you can put charges where you don't want it. You can short. You can have charges leaking around the side. It really messes with you. So to do things in air is a bit more complicated than vacuum. Vacuum, you don't have to worry about that. Moisture is the biggest killer, especially in Florida. So you want to do stuff in a very dry environment or high vacuum if you can.
So you're saying that in a vacuum chamber, you get more thrust.
You could make a system work better. Yes.
Interesting. Well, that's Townsend Brown also said you'd get more thrust.
You get more thrust because the field limit is not 10 to the 6th anymore. It's 10 to the 8th.
Right.
So that's because the forces are related to pressure. They go up by field squared. So instead of 10 to the 6th squared is 10 to the 12th, 10 to the 8th squared is 10 to the 16. So now you have 4 orders of magnitude potential higher thrust just on the exterior part of your thrusters.
So there's more to draw from the field.
That's right. This is a field effect. It's not a voltage effect.
It's fascinating. Yeah, it's so interesting. And but it really flies in the face of the debunkers saying that it's attributable to ion wind because in an environment where there is less ion wind, you are getting more thrust. And it might be due to this field effect, but still you're controlling for the ion wind, which is what they're saying is accounting for the thrust.
Yes. And you have to also, when you're in a vacuum chamber, now you have a new falsity, which could be the walls of the vacuum chamber, giant metal ground. So you want to make sure that you put your test device, whatever it is, in the side of a Faraday cage, and then you measure the force on the Faraday cage. Nothing else. Not what's inside of it. The whole box has to move. So you got to measure that. That makes sure that what you're seeing is real. Then you got to turn that sucker around so that you're not being attracted to the wall through the Faraday cage. Right. So you want to make sure you're always going in the correct direction.
So describe the current kind of state-of-the-art experimental setup on this.
So that's basically what I was saying. Okay. So we'll put it in a box. It'll be a Faraday cage. A lot of ways to make Faraday cages. Ground it really, really well. If you do have voltage coming in from outside, or if you put the voltage inside, you have to make sure it's shielded really, really well. You don't want any Coulomb attraction to the walls or the housing or anything like that. We've gotten good where we've lowered our voltage way, way down. We don't need 30, 40,000 volts like we did 10 years ago. Try to keep it all contained and then reverse it, make sure it works. Put it in air, see if it works. Put it on the mass, put it on the scale, see if it works. Do the pendulum, do the rotator, do the spinner, do everything to make sure it's real because we hate falsities. We hate them. We don't want them.
Okay, so what we have here is a thruster that is set on top of a scale in room air.
Okay, so what Buhler is basically saying here is that he's testing a small experimental in-air thruster to show that it actually works. His team puts the thruster on a sensitive scale. Next, they connect it to electricity, about 480 volts to be exact.
If you look to the bottom right of the screen, you'll see the voltage that is applied. You can also see the current in the center, the electric field, and the runtime. So this is a 42-minute video that we sped up to 5 minutes.
They watch to see if the scale reading changes as a result of the thrust.
We turn on the voltage here, it's about minus 480 volts.
When they turn the power on, the thruster produces a tiny force.
Within a few seconds, the force starts to be applied to the thruster, which is on top of the scale, and it goes in the negative direction, it's lifting up.
They're specifically demonstrating that the force is real and controllable, enough to lift about 0.1 grams.
When we see about 0.1 grams, that corresponds to about 1 millinewton of thrust.
When they turn the power off, the force goes away.
Okay, so we leave it on for a few seconds, and then we turn it back off, and then you can see that it'll come back down.
They repeat this to show it's not a fluke.
So what we'll do is we'll do this again. We'll turn it back on, get it back up to the millinewton range, and let it sit for a few seconds. So what we're showing is that you can actually turn this force on and off.
They then flip the thruster upside down and run the test again.
So you'll see that here in a moment. And the reason why we have it off the scale itself, we do not want any attraction of the thruster to the scale itself. Although the fields are very, very weak, and in most cases there is a Faraday shield, we also want to make it so that it's very, very far away.
Finally, they take full precautions to make sure nothing else is affecting the measurement.
So we flip the thruster, we deionize it, basically we ionize the gases, we neutralize any charge that escapes, and then we re-tear the scale. It's typical, is what's needed for scale testing. This thruster itself is surrounded by ground plates, so we try to minimize the field that escapes, but just in case, we neutralize it anyway. And then we turn the voltage back on, in this case about 480 volts or so, wait a few seconds, the thrust kicks on, and then we see the force is in the positive direction, so now it's being pulled down.
Now the force pushes down instead of up. This proves that the thruster itself is creating the force, not some outside interference or attraction to the scale, like electrical interference, or the thruster just sticking to the scale. I would say this video proves the force fairly definitively to any skeptic, but you could technically say that this experiment requires a vacuum chamber because open air can get ionized. Again, ionized wind can result in thrust based on Newton's classical laws, but 480 volts isn't nearly enough to ionize the air, so it's kind of a moot point. But just for good measure, here is another variation of the experiment, also showing thrust, this time in a vacuum chamber.
What we have here is a vacuum test highlighting actual movement in vacuum using a dual thruster pack in the vertical spinner orientation. And how we measure the forces here is we have pegs at the bottom of this stand that are about 2 millimeters apart, and the deflection, once the thruster is turned on, moves at about 14 millimeters, which corresponds to roughly about 2.5 millinewtons of thrust when we turn this device on. These devices are actuated externally to the vacuum chamber through a Bluetooth connection, so they're not in contact with anything, but the ITO walls that surround the thruster pack, shown by that clear transparent plastic, is perfectly grounded, so that eliminates Coulomb attraction to the wall. We're also in high vacuum, so there's no ion wind interference. Just to highlight that these thrusters are actually developing thrust internally, not an external effect. So power systems inside the chamber, all the high voltages encased, surrounded with an indium tin oxide sheathing, and the thruster does come on as expected and go off as expected for these earlier versions. So that is a nice way to show that there is actual physical movement in high vacuum. We're not just recording force measurements without actually corresponding that to real force.
So these are just 2 out of the 2,000 experimental variations from Charles, Drew, and the Exodus team. If you're an experimental physicist with a credible background, maybe you have a PhD, or you're a professor at a top 200 physics department, and you're a bit bored and interested in exotic propulsion, and you want to see one of these experiments with me live in person to help vet it and maybe change the world in the process, hit me up at usa.alchemy@gmail.com. Skeptics are extremely welcome. I want people who are in good faith trying to poke holes in the experimental setup here. If I were to pluck a random experimental physicist from an elite college and place him in front of this experiment, the exact experiment you just described, is there anything they could say to deny the empirical effect that you're seeing?
I honestly don't know. I mean, as far as we can tell, in the electrostatics community and with my colleagues, because it's DC, that eliminates all the magnetic effects. So you can get all kinds of weird stuff happening when you have magnetics going on, Earth's magnetic field or whatnot. So
and DC is direct current. Are you saying if you had alternating current, you'd have weird magnetic field effects?
So you'd have to account for any fake readings with that. Yes, if you have AC, sure.
Interesting. Okay,
DC eliminates a lot of that.
Yeah.
And then when you turn it off and it's still there, that eliminates a lot of that. Right? So now you really are scratching your head like, what is happening here? And that's where we're at. Like, what is happening here?
Is there anything that they can hang their hat on as far as being skeptical about this actually happening or being able to explain it away through prosaic physics forces that are known?
I mean, I think if you look at every single experiment, you can say, well, this might be fake because of this. I say, okay, we'll put it over here. Oh, well, now it's maybe fake because of this. Okay, we'll put it over here.
Yeah.
So show me a rock. What about this? Okay, now do this, do that. So
is there anything left is what I'm trying to ask you. Like if you had to stress test your own.
If there is, it's something quite exotic that I have no idea what it would be. I don't know what else it would be.
It's shown itself over and over again. How many variations of this experiment do you think you've tried sequentially from 2010 till today?
Since Drew and I, we've been keeping track. We are close to 2,000.
Oh my God. 2,000 instances of the experiment or 2,000 variations?
2,000 variations.
Holy shit.
2,000 test articles. Each one is tested multiple times.
Whoa.
Folders of folders.
Has anybody come in, thoroughly examined your experiment, and come out skeptical? Or has everybody that's thoroughly examined it come out saying there's something here?
I would say the latter, for sure. There's something there.
You cannot think of one person who is still like, I spent, a day plus with the team and I still, think I can explain it with some other, force.
I haven't
or with some conventional
anyone.
force.
I can't really think of anyone. Granted, there's not been that many people have seen it, a couple of dozen or so, but I don't think so. What's really cool though is some people have called me up and say, I represent an investor. I would like to. The investor would like to, invest into your company or whatever. I said, okay, well, what you have to do is you have to fly down, you have to see it, you put your hands on it, and usually that's the kind of the routine. He said, oh, I don't need to do that. I said, what do you mean? I already built one in my garage. I got a 1 millinewton. You showed us how to do it, so I just did it.
Wow.
So it's been the opposite. People have been very taken into this, and they're very excited about it.
That's amazing.
So the people with the know can do it. And the people that have seen it, I just don't know if they know what they're seeing, but they definitely like it. And they're probably not good enough to vet it, I would say, because vetting it would take a lot more work. And I think it would take a lot more expertise. We haven't had too many, other than, Dr. Clements, and there's other physicists that have seen it that have said anything negative about it. We haven't seen any that have said it negative, but we haven't seen, it hasn't been exposed to the entire scientific community either. I think in this field, it's hard to find who are those people, like who would be interested in it. My hope is, and one thing I did want to mention is,
I think everybody should be interested in it.
Well, I think so.
Yeah.
When we are hosting the Electrostatics Society of America conference this year, my lab is, that's in Cocoa Beach, Florida. And I will do a live demo of this.
When is it?
There in June.
Can I come and film?
You can.
Oh, it'd be amazing. Let's go. I'm so excited.
The Electrostatics Society of America is just it's called the Friendly Society.
Cool.
And this is an electrostatic phenomenon. So, I'm going to highlight how electrostatics is so necessary for space. And propulsion is one of the things I think it could help for sure. So I'm going to mention that.
Why don't you submit this to peer review and try to get it kind of academically checked off?
I'm trying.
Okay.
It's just a very busy person.
yeah, you're busy, but I want to see this destigmatized.
I know, I do too. But, there's the path. Right now we're focused on getting the company started so we get some funding to really get the forces up. That's our main focus.
Yeah.
The peer review and all of that's going to take 20 years. So I'm starting that.
I don't know if it'll take 20 years.
Maybe 30.
What?
It just will. It just will. It's too different. It's
because of the antibodies.
Yeah. This field's been poisoned multiple times for a century.
I would say that. And then I think people are becoming more and more open to these sorts of effects. Are you familiar with Sonny White?
Sure.
So, he's
I haven't met him, but
he's another NASA guy, NASA Eagle Works. And
yes.
he is kind of similar to you where, he has this kind of pretty credentialed, impressive background. And he's claiming to 1.5 kilovolts, powering up a little microchip based on the Casimir effect.
Yeah.
And the Casimir effect is this long, legendary kind of anomalous effect that if you were to walk into elite physics, departments, I don't think you'd get too many people denying the effect itself, but it's essentially two not charged but conductive plates, and it seems like there's some sort of maybe quantum vacuum fluctuation thing going on between them, and the plates attract in this sort of anomalous, interesting way. And he's claiming to be able to tap into that, which is, I hate the word 0 point energy. The term, is so quacky, but it is that. And so you have that. You have Beatrice Villarreal. I don't know if you're familiar with her, and I don't know if you're into UFO stuff. I don't want to muddy the waters too much, but she's at Stockholm University, and she's, again, like traditional astrophysics credentials, really impressive, astronomer. And she went back and looked at these plates from the Palomar Observatory, which is, was the most in use observatory in the late 40s and early 50s. And she looked at the plates from 49 to 57, so pre-Sputnik, and she found all these transients, these light-reflecting objects that are flat and mirror-like and seem to exist somewhere, probably in geostationary orbit, so kind of like outer, Earth orbit.
And these short flashes and not streaks, they're associated with things that are extremely flat and extremely reflective.
Wow.
Like mirrors. And that makes it more fun.
Like mirrors. And they're exactly how all the early CIA documents would describe UFOs. And they show up 68% more around nuclear detonations, which is, we know UFOs are kind of attracted to nukes.
Out of those 2,700 days, if there's no nuclear test, there's a transient on 11% of those days. But if there's been a nuclear test the day before, then it's almost 19% of those days have a transient. So that 11 versus 19 is about a 68% increase in risk for a transient if you've had a nuclear test.
And she got that passed through peer review. So I don't know. I think the world is opening up to this stuff. And my hope is that 30 years is a way overestimate. And I hear you. I mean, academia is totally close-minded and dogmatic, but I think maybe sometimes you just have to walk through the front door. You just have to like knock and they'll let you in.
Well, I'm gonna be the front door. I'm gonna be the house that lands.
I love that.
Peer review in a paper, the physics people are gonna debate for decades.
Sure. I
like having the website and Drew and having videos how to make the things. Go ahead and make them.
Yeah.
If you don't believe me, go ahead and make them in the garage.
Yeah.
This has been very helpful.
So
people have done this.
So you'll do this like you have like these DIY videos where it's like, go do this at home.
Yeah.
Whoa. And where are these videos?
They're on our website.
Oh, wow. And where is that? Is that ExodusSpace.com or what? Or
ExodusPropulsion.space.
ExodusPropulsion.space. Okay, check that out.
Yep.
And you've shown your experiments with all of the configurations that would...
Not all of them.
Okay.
We have to keep some stuff quiet.
Okay, cool. So are you doing like lateral propeller experiments, or are you doing things that involve like lifting objects?
We're not lifting objects yet in Earth's gravity.
Okay.
We're measuring the forces of these objects.
Yeah.
And seeing how much their force can lift as compared to Earth gravity.
Got it.
So we do have thrusters that are theoretically capable to lift themselves up. The problem is all of the hardware that goes with it, the voltages and the powers and the wires and the framing and all that other stuff is not there yet. So you have to, it's like saying your car engine can lift the engine, can move the engine down the street, but no tires and no frames. And it's not very useful.
Sure.
But for right now, for what we have for lunar applications, space applications, it's awesome. It would be fantastic.
That's amazing. So in microgravity or no gravity environments, you'll get a ton of thrust.
Sure.
That's amazing. And you're seeing weight reduction. Is that right?
Well, we were saying that, the weight reduction would be something we're seeing, not mass reduction. Be careful.
Okay. Yeah. No, I know that gets thrown around in UFO world all the time. You're
All
like,
the time.
wait, are you you're reducing the
Negative
mass of
No,
the thing?
it's definitely not negative mass.
yeah, right.
But yes, we do those tests. We have videos. I can share some with you.
Please.
Where we put stuff on a scale and we turn it on. It gets lighter. You flip it over. It gets heavier. We are going through a peer review.
Okay, amazing.
For our second patent. So the
cool.
examiner's office is doing a thorough peer review. They're the ones going down that path.
Okay, great.
Which is apparently equivalent to a scientific peer review. So that's what I've been told.
Amazing.
So they're reaching out to people that have done it, reaching out to people who have signed affidavits to say, yes, I've seen it. Yes, I've reproduced it, blah, 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 blah. So they're going through that process now.
What inspired you to pursue kind of more exotic propulsion to begin with? Did you have any childhood experiences around this sort of stuff?
Yes, I did. I've always had a fascination with UFOs, and I think it's been around a long time. Just strange phenomena, but I think it really hit home. I think I was 11 or 12 when we worked our haunted house. My dad would make haunted houses in our garage in New York.
Really? What does that even mean? Make haunted houses in your garage?
Built a haunted house for the hotel that he worked at. Giant Holiday Inn, I think it was, or Hilton in Connecticut. And it was a massive haunted house. And his job was to build the whole darn thing. So he liked that. So the next year we did it at our house. And we charged people like 50 cents to get in and go through the haunted house. And it was probably, I think it was a 9x11 single car garage haunted house. And we made $1,100. So many people showed up. It was crazy. It was a lot of fun. But we had a haunted house and it would go on for several weeks. One night while I was there working it, a whole bunch of cars came into the driveway. And I recognized one of the kids getting out of the car. He said, "Charlie, go look at that." And he shows me, we look up and there's these 6 bright white lights at the top of the trees, just hanging over the trees, just going over the road, just, not moving very fast, just hanging out in formation. No sound, no wind, no nothing. And all these cars were following these lights for several days. This happened over a course of several days.
Was this
every
like
night.
A famous UFO wave or flap or something?
It was. It was in the papers and all that jazz. Southeast New York in the mid-'80s. It was a lot of fun. I thought that was pretty cool. So I kind of geared my career towards trying to understand some of that stuff. I just wanted to know what the heck that was. And it got me interested in physics, I think, and science in general. I was always interested in science.
Did they look like orbs, or were they part of a formation, or do you think they were part of the same craft?
I think they were different craft. I think they were just separate crafts.
Wow.
I didn't see a solid object or anything.
And so this was for days at a time. And
they would come every night. They'd come back and they'd be in different parts of the city. I don't know what the heck they were doing or why they were there, but it was pretty cool, pretty wild. It was about the same time where somebody said they saw the Men in Black, which I thought was hysterical.
Wild.
Because I was, we were trick-or-treating out with my friends, and we ran into another group of friends, and that group of friends said, "Hey, these 2 weird guys showed up in these 1920s outfits." And they said, if you see something weird, they said, just close your eyes and tell it to land. Do you guys know what the heck that means? I knew what it was. I said, "Where are these guys?" "They're right over there." So we went running to go look for them, but I didn't find anybody.
But you knew of the Men in Black.
I knew the phenomena. No one knew what the Men in Black were in the 1980s, early 80s. I don't think that was a thing, but I'd like to study that stuff. So I knew who that was or what that was.
That's fascinating.
So I thought, oh, this is cool.
How can we learn more about this UFO flap? Does it have kind of a name that it's been kind of preserved by, or is there a way to search it, or?
You could just look at Brewster, New York.
Brewster, New York. Okay.
Probably 86 or 85, somewhere in that range.
Wild.
Newspapers and television almost weekly carried reports of the sightings. From different places throughout the area, eyewitnesses all reported seeing the same thing.
I looked up, and right over my head, virtually, and it wasn't far off, it was right over my head and very still, there was a rim of lights in the shape of a triangle.
It was just a tremendous object. It was anywhere from wingtip to wingtip, about 50 or 60 yards.
These were very, very unusual lights. I've never seen anything like it in my life. And so I pulled my car over and I had to take a look.
But it was in the paper. I remember that because it lasted several days.
And you hinted to me that you had an even more surreal experience.
Yeah, that was not a surreal experience. That was just me seeing some lights.
That's surreal for many people.
Just lights. It was lights, but yeah. I had a more intense experience, I would say, many years later. My wife and I experienced this. And it was a pretty cool event now that it's over. A little terrifying at the time, but we live in Cocoa Beach. So we went out to the beach one night, I would say 9:30, 10 o'clock at night. And we're the only ones there. It's not uncommon, though, back then. This is maybe 10 years ago. And maybe 12 years ago. So we live close to the Patrick Air Force Base, which is south of us. And so out in the ocean, maybe about 3 miles south of us in the ocean, I would say about 3 miles. We could kind of gauge how far things are apart because we're used to all the rivers and they're all 3 miles wide. So this is about 3 miles out in the ocean. We see a red light, just a beacon, just bleeping. No big deal. Just a boat. Thousands of boats. But not that night. There were not thousands of boats. And it gets brighter and it gets brighter. We're like, man, it's getting kind of bright. What is that? What, beacons don't get that bright. So it's got to be a boat. Maybe someone's in trouble. And then it gets really bright. And then it explodes. So we see this giant, I don't want to say mushroom cloud, but it got very, very bright. So bright, it lit up the whole beach as far as the eye can see, all the way from Cape Canaveral all the way down. And I said, my God, what the heck happened there? My wife and I were like, that's crazy. Clearly someone's going to call the police and tell them that a boat exploded. We're on the beach. We didn't have phones or anything at the time. Like, what the heck is that? So I would say 5 minutes later, wasn't that long, 10 minutes, we see one of the helicopters from the Air Force Base go out to it. So they get up and they fly over it. And they hover right over it. It's still blinking. It's not exploding. It's still there, still blinking. Just a nice pace. Bling, bling, bling. Helicopter hangs over it, looks at it. Doesn't do anything. Goes all the way back. So like, well, are they going to help the people? Are they going to rescue them? Or are they going to do any of that? Nothing. That is so weird. That's when it got fun. So now, as we're watching this thing, it's about 10, 15, 20 minutes into it. It gets closer. Still blinking. It's getting closer. It's leaving. It's moving. And then it gets within a mile. So it was at 3 miles. It was to 2 miles. It's to about a half a mile. And then somewhere at, I think about a half a mile, it's not one light anymore. It's split into 6. And it's not just getting bright. These orange pinkish lights split and then they started rotating. And they just started rotating like bicycle spokes on a wheel. And they kept getting closer. And they would go under the water and come back out. Under the water, come back out. Under the water, come back out. Like, this is really weird. And they got closer to us. So when it got about a quarter of a mile or maybe 1,000 yards out, we're like, okay, we're going to walk up the beach now. That's been fun. That's a little bit too close. It kept following us. It got closer. It got closer. It got brighter. It got brighter. And I think it was about when they got about, I wouldn't even be exaggerating if I said 50 yards. When we got that close, I started getting a little scared. And I know she was getting scared. Then, after about 40 minutes of looking at these lights and trying to run from them, but not full out sprint, but kind of just walking super fast, like 12 blocks, it went out. And then we walked home. And it was terrifying, but it was not super scary, but it was scary enough because I didn't know what the heck that was.
That's wild. What year was this?
Probably 2013.
Okay.
Somewhere in there.
So you had already started your work on the more exotic propulsion stuff.
Probably, yeah. A couple of years in by then, for sure.
That's fascinating. It's so interesting. So you saw this thing out in the distance, and then it started to loop in and out of the water. and then and approach you, and it got to like 50 yards-ish away.
Yeah, it got really close.
Could
like
you
beyond
make
the
out,
waves, like where the waves started?
Did it still look like this amorphous light at 50 yards, or could you make out the structure?
I couldn't see a structure. Just 6 or 7 lights going in a pattern, faster, slower, in and out of the water like the water wasn't there. And just, it was responding to us.
Really?
Like.
Why? So why? Because that's a common thing for people to say who've had UFO experiences.
It just, if we went up, it went up. If we went faster, it went faster.
It was mirroring you.
It was mirroring us. Did
you get any sort of consciousness download or feel mentally locked in with it or anything like that?
No, I don't think so.
These
lights are kind of common over there. If you study these type of lights, because we live near a cruise ship, the port, so you'll see a lot of videos online with these lights. Stephen Greer takes his group down there to that same, almost that same beach, about 40 minutes south, to look and kind of conjure up the lights. So that, and I have had other friends since then have the same experience or similar experience, which I thought was super cool because he was out at the beach with his family and they saw it late at night. They're the only ones on the beach. They saw them too. This is like maybe 7 or 8 years later. So it's pretty weird stuff that's happened.
What do you think this Patrick Air Force Base helicopter was doing? Do you think it was doing recon on this UFO or?
I have no idea.
Oh, it's so interesting.
The way it behaved, it was just like, oh, it's these darn lights again. It didn't act.
But it looked like it was intentionally dispatched from Patrick Air Force Base.
After that very large, bright event, which was blinding to look at, is how bright it was. They addressed it and went out there and looked at it and still saw it there, getting bright, dim. It was very bright still, not blinding bright, but it was very bright. And it just, that's good. And just went back home.
Do you ever get one step kookier and say, why did this happen to me? Does it have something to do with the work that I'm pursuing?
I don't think so. It happened to a lot of people have seen these things. These lights, they follow cruise ships and boats. There's a lot of weird videos of it. So they're probably just chasing people.
Yeah.
If I had to guess, I don't think I'm anything special. They're just following people.
Well, I might follow the person who's working on interstellar propulsion a little more disproportionately. Did you know that Thomas Townsend Brown had a very similar experience?
Oh, really?
Catalina Island, and a little orb light approached him, literally came up to him. Townsend Brown had a UFO experience in Catalina as a teenager. Is that right?
Yes, and I know the exact spot where he was standing. I used to ride my horse up that ridge. It approached him. It actually approached him.
And
he said that he learned so much standing there with that ball of light that he went back to which at the time was, he had a lab in Pasadena that was funded by his parents. So he had his own private lab, and he said he went to work immediately, and he worked. That was the beginning of his life's work. And he said that everything that he ever learned about his work, he learned instantly.
Wow.
Everything.
Wow. So that's so fascinating.
I wish I got a download. I would have been 10 years further ahead.
Yeah. Well, maybe you've gotten a lot of downloads and you just don't know it,
Yeah.
It's always interesting how, science is treated like, oh, you're just figuring this out. Like you figure out the last, term of an equation on a chalkboard or something. And often if you were to probe the scientist, in many cases, I don't know if this comports with your experience, it's far more like revelation. It's like, it just hit me.
Yeah.
It's Dirac. We were talking about Dirac, staring at the fire in Cambridge and just downloading the Dirac equation, or Heisenberg at Helgoland, figuring out quantum leaps and, probability matrices or whatever around, electron shells. And so this is a very common experience. I don't know if you've ever had anything.
I would say, yeah, some of the math is just very discretized. Oh, we'll try this, and big leap there. And
yeah.
And then months go by. Oh, do try this. Oh, yeah, that works better. That makes more sense. Whether it's experimental or theoretical, it's not a super gradual thing.
Yeah.
It does have step functions to it for sure.
I don't think if you put one of these debunker types like Michael Shermer or Neil deGrasse Tyson, I don't think if they were in front of either of you, they would be able to beat you in an argument. Like,
well, the argument to have to anyone, just go try it.
Go try it. Yeah.
Seriously, don't take my word for it.
Yes.
Go build this thing in your garage.
I think they'd be too arrogant to show up, but I think if Neil deGrasse Tyson were in a room with your experiment, I don't think he could explain it. And that seems like a really important fact, that you have one side that's like showing an effect. You have 2,000 iterations of that effect. You are an expert in this field. You've contributed two, really important things to the field itself that are conventionally now, accepted. And you say you're getting an effect, and then you have somebody else who's just smugly dismissing it. Like, I'm going to go with you over the smug dismissal.
Well, that's how science works. It is inherently skeptical.
Yeah.
You got to understand everything, the theory, the modeling, the experiment. So I expect it. This is why I didn't go the peer review route per se. I went the other peer review route, which is through the patent office.
It's a good, that's a good attitude to have. And, the patent office, there you go. It's smart. Yeah. Just make money off it. Just commercialize it.
Let's just do that.
And if they're wrong,
there you go.
You win in the free market. And no, totally.
So it's still peer reviewed. The examiner's office is peer reviewing it. So
yeah.
But in the meantime, I'll just keep building away, keep trucking away.
Having said that, I like, Thomas Kuhn talks about, in the Structure of Scientific Revolutions, how science moves more around politics than it does truth. And I do think the fact that you lead electrostatics at NASA is this really important thing. There is the kind of, patent, commercial route that you can take. You can just do the kind of startup thing and just win on your own. And then there's another part of me where I'm like, Niels Bohr didn't create the first semiconductor company. And, if you really are, contributing to fundamental physics in the form of this new force, I like that you're coming on this show and that you have videos and you're telling people to do it at home, because it's hard to know where that even leads. And I hope you know that.
Sure.
And so I do think you just letting this out in a public way, I think also will amount to a Cambrian explosion of people working on new, cool ideas. And I think the more you let it out, the more you become a lighthouse for, like, you kind of did it first, and the other high agency people who do other variations of what you're doing will come to you. And so I think it's this flywheel where I do think being public about it is really the right thing. Because God forbid, you have like all these other scientists that spend like their lives in secrecy. And then sometimes they, the frameworks that they've helped establish just kind of go away, and they're still stigmatized to this day. Townsend Brown being a great example.
Yeah,
so
I agree with that. I think getting it out there, letting people see it, this is something that's just too important to be bottled up completely. Really, let's be fair. This is a new force. It's just what it is. Whether it's a gravitational force or some other quantum mechanical effect, it's too important to just say, no. I'm going to work on it until I'm done, then I'll let you see it at the end. That's not what this should be.
Yeah.
We need this.
Yeah.
We need it. We need it now. We say we have an energy crisis. Oh my God, the energy crisis. Well, it could be considered an energy crisis, but it's really a force crisis. It's a transportation crisis. How do you get an object from here to here? That is the real problem.
Absolutely. And we've been flying with Boeing 747s or equivalents, for the last 60 years. It's just crazy. We've seen total stagnation in the world of transportation. And so
the world needs this.
The world absolutely needs this.
So if I can help, I will.
Well, I love that attitude. That's awesome. You mentioned a second patent. Your first patent, there was a national security hold on it. Is that right?
We don't know.
Okay.
But it's possible.
What does that even mean?
Some patents apparently go through the Department of Defense.
Okay.
Before they're released, depending on the nature of the patent.
And some never see the light of day, right? There's the Invention Secrecy Act of 1952.
Yeah, I believe that was one of the risks that we were aware of.
Mm-hmm. Fascinating. So this is the weird thing about these sorts of experiments. There is so much smoke, not only from you. I know a lot of engineers who've worked at aerospace corporations, Lockheed, Northrop, those sorts of companies, and they give you a little wink, wink, nudge, nudge. They often can't say that there's anything to, the Byfield-Brown experiment, but it's often you're on the right path, buddy, and there's weird things happen with high, electric field strengths at short distances and with, big gradients or, asymmetry, that always comes up. And there's something going on. Am I wrong to say this? Because look, a lot of the physics is above my pay grade, but there is just an overwhelming amount of circumstantial evidence that there's a there here.
It seems like that.
Have you met others who've probably converged across the same force that you have? They've kind of stumbled onto it.
I have to think about that. I can't think of anyone off the top of my head. But it's possible. To be fair, I haven't done that much research on the electrogravitics and all those folks. I've started reading some of the books, and there are a lot of books on this stuff.
Yeah. Oh, there are a ton of these books.
And everyone has a theory, and I just have to sift through that to see where are the experiments.
Yeah.
Because, the old adage is everyone has a theory, but no one believes a theory.
Yeah.
But the experimenter doesn't believe his own experiments, but everyone believes the experiments.
But if you look at how science gets pushed forward, to me, the experimental physics is a bigger tell. That the theory is like a prison or something. And so I never like, this can't work because theory.
Yeah.
Like, I think it's, this worked, and we have to explain it with a new theory.
Yeah.
And it's like the Casimir effect, or like and maybe the Casimir effect makes sense in quantum electrodynamics. I don't know. But there are a lot of these, what's a good example? Like blackbody radiation in the 1860s with Gustav Kirchhoff. It should have produced this ultraviolet catastrophe, and it didn't. And it was because of, quanta, which Planck discovered 40 years later. And so there are a lot of these sorts of examples, and you can't say the anomaly isn't right because of the theory. And there's just so much anecdotal evidence around this anomaly working.
Yeah, I think there are examples. I gave some of those in the APEC. Some of the examples of how this force might manifest. You don't even know that you're seeing it. Like momentum anomalies for spacecraft when they go around the Earth and they get to the Van Allen belt, they either speed up or they slow down just by going through picking up charge as they go through the Van Allen belts, which doesn't make a lot of sense. So they have to actually add extra fuel to spacecraft to account for that. They don't know where it comes from.
That's fascinating.
So there's all kinds of things like that.
So those momentum anomalies are possibly attributable to this force.
I think so. It's possible.
And you're calling this the Exodus force, and your company is Exodus Space.
That's right.
Okay.
Well, the force is really two forces. There's a surface force and a volume force. We call the surface force, that's actually electrostatic pressure force, just because it comes from electrostatic pressure. And then we have a divergence in the E field force for the volume element, because the integral has a surface and a volume component, at least the classical version, which is not truly correct. It's close, but it's obviously you can't explain this force, I think, in classical mechanics. You have to use quantum, but at least the classical kind of steers you in the right direction, because you can actually build something on that to test it. But to be fair, it has to be a quantum mechanical effect. It's not a classical effect, what we're seeing, which has always been known.
Why are you sure it's not a classical effect?
Well, for one, we're not conserving energy in the classical world.
Right.
If we put something on the scale and we turn it off, it should go off. Because the fields are intact, the force remains. So now we're dealing with something else, just like the Casimir effect. It's dealing with something else. You don't need power for the Casimir effect. You can just put two plates in space and they will attract. You do not need to add power for that. It is an artifact of the structure of the vacuum. This might be another similar thing, just in a different light.
In the Townsend Brown experiments involving electrogravitics, they were capacitor experiments. So you had a negative electrode, you had a positive electrode, you had a high K dielectric in between them. The high K factor, which is the ability to store and discharge easily a lot of, high electric fields, was this really important factor for determining the thrust in the experiment. Does that make sense in the context of your experiment?
Sure.
Okay.
So usually if you have a high capacitance, you can store more charge, right? some more charge, more energy. But we have to look at, we look at all the capacitances, not just the capacitance between the two plates. We look at the fields and how you can strengthen the fields. Sometimes high capacitance or high K values, high dielectric constants can lower the fields. So you want a high field, depending on where you want the thrust to be. So you can tailor some of that with capacitance, just like Townsend Brown did. But it is a field effect. So those are the things, those are some of the knobs you have. You have a lot of knobs. You have geometry knobs, capacitance knobs, voltage knobs. You have a lot of things that we can do. But how you can explain this force classically, I don't really know, at least with the conservation of energy stuff.
Is Brown would use DC pulsing and kind of high climb rates of the voltage. So that the voltage there'd be a steep climb rate where it would, increase very, very sharply. Is that also consistent with your theory, or?
I don't really know. I mean, we try to stay away from the AC stuff or the very high slew rate stuff if we can.
Yeah.
Damages to the plastics or damages to the metals, damages to the materials, too much current. We haven't explored all of the different ways to actually enact it. We're still exploring the DC versions. We haven't explored all the different ways you can apply different voltages and different currents to it, which is something we have a lot of room in the future to improve upon. But we're doing so many variations with all the other parameters. We don't really need to change the slew rates too much yet.
Do you take issue with the term antigravity, or?
I don't like antigravity.
Okay. Well, because that would be like an opposite of gravity force. Or
or the like the electrogravitics. It's very pretentious to say that we're messing with gravity.
Yeah.
Even Drew calls us warp drive. I'm not there yet. I'm not there yet with the bending of space time.
Yeah,
there are experiments to check that. You can use interferometry or something like that, and I believe the Apex folks are looking into that. So we'll see what they find. But I don't know if we need to. I don't think I'm bending space time with my my 2,000 volts and plates and wires and needles. I don't think I am. Maybe I am, but I don't think I am.
But you do think you've discovered an inroad towards propulsion mechanism that could get us into kind of interstellar travel and actually deep space travel, which that's amazing.
Yes, but I don't know if I'm bending gravity for that or not.
Sure.
I don't want to go there yet.
Yeah. No, fair enough.
Because if that's the case, then you'll go down other paths, other rabbit holes that I don't want to go down. Like, then you can make a teleportation device or a wormhole or this or all that other stuff.
Yeah.
Yeah, I'm not ready for going down those paths yet either.
Have you looked into any of the other kind of exotic physics world work, people like Ning Li or other people who've claimed kind of weight reduction?
Have you heard about that? There's a story about this Chinese scientist that was working on anti-gravity and then vanished.
Yeah, real excited about the spinning superconductor stuff.
Yeah.
Because, my PhD is in high temperature
I was going to say. Yeah.
And I was like, maybe that's a way to shield gravity, something like that. And then someone else, I think NASA reproduced it and they didn't see the effect.
Okay.
So I never did anything with it. It's a very expensive experiment to do.
Yeah.
It's something very large, superconductor, and spinning it. Superconductors are not cheap.
Yeah.
They weren't in the 90s. But I don't know. I haven't seen anything that's definitive.
Yeah. There's this guy Pokletnov at the University of Tampere in Finland who claims weight reduction based on spinning superconductors. And I believe there might be a connection between him and Victor Schauberger, this World War II Nazi. I guess he was in Austria. I don't want to call him a Nazi. I think he was just like a hapless scientist. But he had this whole model for spinning superconductivity. And I believe Pokletnov's father was like Stasi guy who was doing tech retrieval for the Soviets. And so, I think there's some sort of lineage there. Nick Cook describes this in his amazing book, Hunt for 0 Point. Mm-hmm. And then you have Ning Li popping up in the early 2000s. It's a great book, right?
I love that book, yeah.
Yeah, it's awesome. And then Ning Li has, he's amazing, by the way. Everybody should read that book.
Yeah.
Nick Cook is a hard-headed aviation journalist at Jane's Defense Weekly in the UK. And he just stumbles onto all this gravity research in the 50s and then realizes it just vanishes and goes nowhere. And he looks through the entire lineage and he comes to the very interesting conclusion that there's so much smoke, there probably has to be some fire, but like never kind of finds a smoking gun, never knows exactly, what the there is. But it's fascinating.
It is. He eventually is like, it's somewhere in America.
Yeah.
It has something to do with 0 point.
That's right. That's right.
And that's where he ended it. So.
Do you think that in the black we've discovered some of this stuff?
I honestly don't know.
I
don't know. I just don't know.
Has the DoD ever reached out to you? I guess the Department of War now, or the Pentagon, or DARPA? Have any of these organizations reached out to you?
No.
It's so strange.
It's very sad. I was hoping to be, taken away and work on some weird UFO project in the basement.
I know. Well,
hasn't happened.
I mean, if anybody should, deserves it, it's so weird. It's like they already know and are miles ahead, and they're sort of gaslighting and waiting for us to catch up, or they're brain dead and it's just bureaucracy.
Yeah,
and I don't know if you lean on either side.
I don't really know. Like your last interview pointed out how few physicists there were for the retrieval program.
This can't add up. It's a 2-line proof. It defies the laws of physics. We haven't made progress. We have no physicists.
I thought that was very interesting because my wife and I were approached to help with the UAP. NASA was doing their own UAP thing. And they finished one report, and then there was a second one, a second follow-on.
Really?
I forget the name of the gentleman who reached out to us saying, we're doing this investigation again. I'd really like your help. I said, oh, okay, just put me in with all the physicists. Oh, there are no physicists. What do you mean there's no physicist? Why am I the only physicist? And it's an instruments group, so they have advanced instruments to try to capture these sensors or something I'm not quite familiar with. So I don't really have time to join that group. But I was shocked by that too. Like, why are there no physicists here? Maybe I'm missing something.
It's very bizarre. Yeah,
I was like, you would think there would be only physicists.
That was one of the most bizarre conversations I've ever been a part of.
I had to watch that twice. I was like, are you serious?
Yeah.
Why wouldn't there not be any physicists?
I don't know. Either, again, they figured it out and are sort of gaslighting us, or they have this limited hangout strategy where some of the more popular physics frameworks, like you hit certain areas of it and then you get sucked up, or it's brain dead. Or the UFO stuff is so weird and consciousness-based that our physics is so clearly kind of not equipped to deal with it that it's like futile to even deal with physicists. I don't know. But it was weird. You didn't see my Gary McKinnon interview, did you?
I was just a guy, normal guy, interested in UFOs, happened to have some IT skills, nothing genius level.
You hacked into the Army, the Navy, the Air Force, the Department of Defense, and NASA.
Do you know who that is?
The name sounds familiar.
So this is a guy who he lives in the UK. Mm-hmm. He was, in 2001, he was like in his girlfriend's aunt's basement at 4 a.m. smoking weed, had some IT skills because he worked with a bank, and was a UFO nut, obsessed with UFOs. And so did some like basic blank password phishing techniques to essentially hack into NASA, Navy, Army, CIA, DIA, like every elite.
Is that the guy that's still trapped over there?
He's still there. Yeah, because there's a live arrest warrant out for him now.
That guy, yeah.
Theresa May, former Prime Minister of the UK, has finally given him kind of, safe harbor or whatever. So he's there. But he's not allowed in the US. He's on the Interpol red list. And he specifically queried when he got in, he was like, oh my God, I'm in. And then he queried the Johnson Space Center because there was a UFO whistleblower named Donna Hare who worked there, who saw basically images of UFOs being airbrushed out in a specific building, Building 8 there. And so he looked in and he saw a Tic Tac object floating around the Earth, like in Earth's orbit.
And the hemisphere comes into view and it's very blocky, but it's kind of blue and white. So I'm thinking, well, it must be Earth. And then suddenly there's a big, straight kind of silvery line that is coming down. Then that's, I guess, what they now call a tic tac, but it's what we used to call cigar-shaped object.
And this was in the early 2000s before David Fravor's sighting at Nimitz. Super wild and interesting. And then for our purposes, why I think this was an interesting conversation is he then stumbles upon a list of non-terrestrial officers, of which there are 40. And it was very strange, right? Because as of now, if you look at, any of the, ChatGPT, Anthropic, any of these things, it'll tell you that we have like roughly 10 people in space, like globally. And so 40 people in space, that's strange, right? And it's the names of these 40 people, non-terrestrial officers, fleet-to-fleet transfers of these specific materials. And a lot of the materials are high K dielectrics. And they seem like these thinly layered materials. And then there was like this one material, I think it's like molybdenum.
Molybdenum?
Yeah, molybdenum. Yeah, there you
molybdenum.
That's molybdenum.
There you go.
And molybdenum is good for like alloying. And so we came to the crazy conclusion on the spot that maybe there is a microgravity space supply chain for materials for these high K dielectrics, which ironically, those high K dielectrics work well for these experiments, for these, again, the quacky word is anti-gravity experiments, for these experiments showing this other force. Okay, so there's like a space supply chain where humans are manufacturing these exotic materials in space that you literally couldn't make
physically impossible on Earth.
On Earth, yes.
Yeah.
That's fascinating. I don't think, has anybody ever explicitly tied together your thing like this, like we're doing now?
No, this is fresh and unique.
I love this. And there are commercial companies trying this right now. So for anybody who thinks we're crazy, like that's a thing. And then what would you do it with first in kind of a more, like covert setting? You would do it on things that are of extremely high value. And, if you produce materials in microgravity, the kind of signal to noise is much better. There's less, dust and interference issues. And so you could do things like, atomic layering, way easier. And so I wonder if there's something like that then works into some of these experiments being done. I don't know if you have a take on that.
There's a lot there.
Yeah.
We're working with high K dielectrics and layering materials and different things, but I have not heard of anything going on in space manufacturing for that.
Okay.
Not on my end.
Okay.
But it'd be very interesting.
Yeah.
Space manufacturing is something NASA is trying to get more and more involved in.
Yeah.
Because of some of the reasons you mentioned. But I've not heard of any spacecraft being manufactured in space.
Yeah. I have to ask you while I have you, what's your best argument for the moon landing hoax people?
I would say that the lasers that are beaming back to Earth, or you can beam there's reflectors. We just put a new one on from Firefly. You can send a laser, it'll come back. So that's been there since the Apollo days.
But you could put a photo reflector up there with the rover, theoretically. So it's not super concrete evidence.
That's not super concrete, but we do have a lot of the Apollo samples.
Yeah.
I have 200 grams or so in my lab.
You have some moon rocks?
Not the rocks, the dust. The rocks were given out to different countries and stuff. JC probably still has some rocks. I don't have any rocks. But
okay.
It's vastly different than the simulants that we play with.
Yeah.
It's got a very high angle of repose.
Yeah.
So basically you try to flip it over. It doesn't want to flip over. It's very jagged. It's very different. It's interesting stuff. There's no doubt it's not weathered.
Yeah.
It's not seen a lot of moisture, those kinds of things. It's different stuff.
Have there been any bad actors trying to kind of come in and debunk in like a bad faith way, or?
I don't think so.
Okay.
I haven't seen any.
Okay.
No, most of the people are, like the APEC folks are they're open to everything.
How do you answer the question, why has nobody done this yet? I mean, the other answer to that question is they have, and we just listed some of the people earlier who have actually pulled off the experiment. But do you have a good answer as to why?
It takes a bunch of things to line up.
Okay.
You have to have high voltage experience because these tests can be lethal.
Right.
They have to be packaged up properly, put into a Faraday cage, or you're going to get fake positives, false positives. to be attracted to walls or floors or ceilings. You have to make sure you're not doing that. You have to prevent the ion wind, which is very well known. Fun thing to make. Does give you some forces, but they're not what we're interested in. So there's a lot of facets there. Then you have to have the technical savvy to, show it in many different ways: pendulums, spinners, rotators, force measurements, scales, all of those things. And each one of those can be fooled. So you have to make sure that you do your due diligence and do not, get any false positives, especially on the scales. Everything has to be shielded pretty darn well.
Can I bring up another thing that I think limits our ability to do this? I think it's the amount of people who think it's possible that there is another force outside of the conventional forces. And so you need a hypothesis to get, a positive result in certain cases. And I think if you are so dogmatically, confined to, very conventional physics, you would never even try this experiment, maybe. And so you have to have the imagination to, realize that there might be a there to even try it in the first place.
That's right. You have to try to do something. If you believe in it, try to do it. Like I did with the field momentum, the linear momentum. I tried that for 15, 20 years. I failed, but that doesn't mean I had to give up. I was still seeing a force, even in that, even if it had nothing to do with that theory. So you keep trying. That's the best thing I can say. You got to keep trying. If you believe it, if you keep trying, maybe you'll see something. Here, that's the case, I think.
And you think that this vindicates the work of Thomas Townsend Brown, too? Maybe he didn't understand what he was dealing with in the way that you do, but
if he says he understood the ion wind like he said he did, I know he did things in oil where you can't have ion wind, then he possibly came across it. He might not be the only one.
Yeah.
People that play with high voltage, with asymmetrical capacitors have been around a long time. So it's entirely possible that
maybe Tesla.
Maybe. I don't know if he did much of asymmetry. He did a lot of energy stuff.
Yeah, I don't know either. But there's actually, you mentioned transmission oil. There's a team in Japan. I believe they came out of Honda, and I think Musha is the scientist's name. And he claims they've submerged the capacitor in the transmission oil, which, apparently doesn't ionize, or at least ionize very well. Yeah. And they claim some results, and they kind of have gone silent. But they never retracted those results. That paper's still out there. So there's so much of this.
There's another group I'm working with in Germany who's reproducing this. So
really?
Yeah. So it's coming.
It's amazing. Well, I'm really excited to get into, you have a whole theory about how the thrust works in your Exodus experiments, and it involves quantum electrodynamics. So I asked you if I could bring a friend of mine, David Chester, who is quantum electrodynamics specialist and a theoretical physicist. And so are you down to have a group conversation? We can change sets and sweet. All right. So we have David Chester here, who's a friend of mine. He got his undergrad at MIT, PhD from UCLA, both in physics, and is kind of specializes in general relativity as well as quantum field theory. But to me, you are the guy who is the kind of intersection, if you have kind of two circles in a Venn diagram, of kind of smartest and best credentialed, who will entertain all of the quacky stuff. And so we've had long conversations about a lot of this, extended electrodynamics and some of these weird topological or experimental physics effects. And you really, I think, understand kind of the lay of the land as well as anybody. And I was speaking with you, Charles, about doing this interview, and you were like, I'm developing this quantum electrodynamical theory of how this actually works. And I was like, I probably won't be able to say anything about that, but David will. So I'm really excited to have both of you. And maybe we start with you, Charles, if you could just kind of present what the theory is, and then you guys can kind of go back and forth.
Sure. No, but this is a good opportunity to talk to a real physicist about my, my proposed explanation for the force that I'm seeing. So I don't like to create stuff up. That's kind of one of my mantras. I don't want to do that. I want to use what's known in the physics community to see if it can explain what I'm seeing. I don't want to be one of those guys, I have to come up with a whole new theory. I don't think that's necessary. So my approach was to say, what are the tools we have now? to try to explain this. Can it be done within conventional physics that we know? Just maybe one other step further, or something, within the realm of what we already know. And we have a lot of tools in quantum electrodynamics. We have a lot of tools. So I started from what I have in my experiments, basically 2 charges. So I have a plus and a minus charge. That's my starting point. I don't have anything else. Not as far as I know. Now, if I'm bending space-time or doing something silly, that's beyond my knowledge. But are there the tools available to understand the forces in just knowing what we know with QED with 2 charges? QED is very, very powerful. I found an example of how QED can solve a very simple problem, which can be easily solved with electrodynamics. So let's make it infinitely more complicated with QED. And that's what physicists do. It's because it's a more fundamental theory. So I started with QED to explain Coulomb's law, the force of attraction, repulsion between 2 particles. So that's very well explained with Coulomb's law. But in the context of QED, I found a book that actually did this. In my grad school, we were not trained how to do that. It's not uncommon. There's a lot of very remedial physics problems that take 2 or 3 hours to solve that are not going to cover in a class. But I saw the QED version of it and I said, oh, this is very, very helpful. I know where it comes from. I know where the I know where the momentums come from. And then you do the math appropriately, you'll get Coulomb's law coming out of it.
And Coulomb's law, for people not familiar, can you describe it very basically?
So basically, it shows that if you have 2 particles, their force is related by 1 over the square of the distance away in relation to the charges that you have. Very simple, rudimentary physics.
And it explains things like electron repulsion to like forces repelling.
It basically explains everything that we know about 2 particles, 2 charges.
Yep.
Just about everything. QED.
Explains how atoms are bound together. And,
sure.
Yeah.
So I did not think we needed QCD, quantum chromodynamics, W particles, Z particles. I didn't think we needed that. We're not looking at the interactions between protons and neutrons. So we're not looking at the high energy realm. We're just looking at low energy Coulombic charges. That's it.
And when you say you're explaining the Coulomb charge with quantum electrodynamics, how is it normally explained?
Usually you'll do, Maxwell's equations or something simple to derive Coulomb's law. It's not very complicated. F equals QE, right?
Yeah.
So we know the electric field is point charge times Q.
And Maxwell's equations govern electromagnetism.
All of that.
19th century.
That's right.
Okay.
But what they don't tell you is how do these particles interact? Like what's causing them to repel or attract? What is the physical mechanism? QED provides us a nice little solution. QED says, well, thanks to quantum or Feynman and Schwinger, they are exchanging virtual particles. So they're not real particles. You can't see them. You can't observe them, but they're virtual. So basically you can picture, this is the cartoon that people use. You have 2 ice skaters. One of them is holding a bowling ball. The first one throws a bowling ball, so they recoil. The second person catches the bowling ball, so they fall back, except there's no bowling ball. So not real one that you can see, but you can see the interaction between the 2 particles. And that's the Feynman diagram. And what you do is each time you write a Feynman diagram, each one of those lines in the Feynman diagram represent a different term, and you multiply them all up, and you get what's called the scattering matrix element, and you can try to find how these things interact. If you were to take this particle A and shoot it at particle B, you could see where it deflects on a board somewhere if you actually measure that. That interaction is all described in that. QED, using QED to derive Coulomb's law is very complicated. But I found a book that did it, so I copied that, looked at what they did, and said, okay, this is a good model. Let me just do one thing different. I don't have just Coulomb's law. I have something else. So what I think it is, and what I proposed now, is what would happen if I just went to the next order. So quantum electrodynamics, QED doing Coulomb's law, is a second order equation on using time-independent perturbation theory. Perturbation theory is the best tool that we have in physics. I think, bar none. Perturbation theory, it's awesome. It's outstanding. It's very powerful.
What is perturbation theory, high level?
High level. So high level, you can get the energy states or the states themselves using perturbations. You just change a little thing. You change an energy state. You add that back in. You do another perturbation. You see how it changes with a small perturbation of the energy in this case, or the states, and evolves. So, and there are many perturbations. So I'm using second order perturbation theory that's the lowest perturbation, and I think the highest perturbation for 2 charges, Coulomb's law. And after that, I don't think anyone's done anything after that, because you not only get a close answer, you get the exact answer. So I was like, why go further? You have 2 particles. They either attract or repel. That's Coulomb's law. Do you need to go further? Not. So I'm like, well, this force with that I've seen with Exodus, this electrostatic pressure force, is much, much weaker than Coulomb's law. There's no doubt. Much weaker. But I decided, well, let's try the third order. What does that give me? And when I tried it with my math, which may not be perfect, I'm sure, I was seeing 3 charges now. So basically, one of the charges was weighed twice, multiplied by itself, and then the third order is being multiplied by the first charge. So there's already an asymmetry sort of in the charges, even with 2 charges, which I thought was useful because I wanted to try to get that with classical dynamics. You can't derive that from classical energy, 3 charges. But the QED was kind of nice to show that. So I looked at that and I said, okay, there's no longer 4 terms like there are in the second order.
What would classical electrodynamics give you, if not the 3
So basically,
charges?
when you try to do conservation of energy, you start with a kinetic energy and a potential energy. And so for adding more charges to a system, you just keep adding more and more charges to a system. The superposition principle adds them all up. It doesn't multiply them all up. It adds them all up. But I needed the addition. I needed the pressure that I'm creating working on the charges that I'm creating. So I have a pressure on one side and charges from the other. So I have a multiplication effect experimentally. So I didn't know how to derive that other than quantum electrodynamics, but classically it doesn't show that. But I thought maybe QED might. And it shows up there. But that was the first thing. And the other thing, there were 12 terms now instead of 4. Because I'm scattering. So what happens in QED or time independent perturbation theory, you start from the 0 of the state, the vacuum state, you scatter to the first state, then you go from the first state, you scatter to the second state, and you go to the second state, scatter to the 0 state. That's just how it works. There's a lot of scattering states and matrices that you have to solve for. Then you multiply them together. So I have 12 terms now. Some of the terms are kind of interesting. It looks like that when you draw the diagrams from those states, that looks like you get the same things you had in second order perturbation theory, where they'll exchange a photon, the other ones will absorb it, vice versa. But there are some states that are a little weird. You'll have states where they'll just absorb or just emit, kind of like the first order, which I don't talk about. But the first order is basically just a charge with a field line, well, not field line, but with basically a charge with the scalar photon. So there's 4 kinds of photons in QED. One of them is real. One of them is observable. The other 3 are not. But
2 of them are real.
2 of them are real? I thought
Yeah.
I only read that there's only one of them was real.
Well, you have plus and minus H bar for 2 different spin states.
Ah, okay. Well, that's cool. 2 of them are real.
If it was massive, it would be 3. But since the photon's massless, you get 2 states. I mean, light is polarized. You can polarize it into 2
Okay,
different
I didn't
states.
know if that
And
applied to photons. Because I just
spin
remember the
relates to
textbook saying only one of
polarization.
them was real. I was like, okay. But anyway, so these are not real things. But in QED, you look at the vertices, and every time you draw a vertice, you conserve momentum at that point. So if a particle comes in, it's, we use these silly fiber diagrams. They're not Cartesian coordinates at all, but they're basically a momentum vector, and then the momentum changes. And when the momentum changes, another momentum is created or absorbed. And that's all it is. You can't think of it any more literal than that. So that's what I see in third order. Third order are these vertices that are either giving out these scalar photons or absorbing them, whatever these things are in reality, is how these things seem to be conserving momentum, if this model is correct. So that's the difference between the third order and the second order, at least what I've found mathematically, is that you don't absorb this, you don't emit this scalar photon and absorb it in the same pairing with the 2 charges. There are cases where the 2 charges emit and don't absorb, or absorb and don't emit.
And what is a scalar photon as opposed to a photon?
It's a mathematical photon. You can describe it better than I can, but it has many names, dark photons.
It deals with
That's different.
Is it different? I think it is. Anyway, I think it's a mathematical term.
Okay.
It doesn't have the polarization that a real photon has, right?
Yeah.
Very different.
Yeah.
It's just a mathematical term that you put inside the matrices and you get the, I don't know how it works.
So what are the what are the
scalar?
It's just scalar. It's just scalar. It's no vector.
Scalar of the Lorentz. Yeah.
So the idea of just emitting or absorbing these scalar photons in this third order perturbation, how does that allow for this effect that looks like this new force in electrostatics, or it looks like anti-gravity, or, you know, what you're kind of experiencing?
Well, what it shows is you have an imbalance. And the system can be made to be imbalanced, which is weird. So, because you're not enclosing, I don't know what happens to these scalar photons, where they go, or I don't even know if they go anywhere. They might terminate somewhere else in the universe. I don't know. E-fields don't do that. They do terminate somewhere. But it does, show this weird kind of, imparting into momentum onto something that is already asymmetric. So it's very odd. So wherever you have these, I think that's where the field is non-zero, where these things exist. Where these things don't exist is where the field is zero. So that's the difference.
And
it's basically an electric field.
And super high level, you end up with this kind of virtual particle transfer, and due to conservation of momentum, you end up with thrust.
I think so.
Okay. And what do you think, David Chester?
Well, first of all, I want to commend you on your experimental efforts. I think you're really brave with what you're doing, and it's quite amazing how much data you guys have been collecting. However, I would just advise you to be a little careful with some of the theoretical claims you're making. Sure. First of all, it sounds like you're saying you can get a momentum. You're getting a kick in momentum in the center of mass frame. However, typically in QED, momentum is conserved and you still have translational symmetry. So you're typically not able to get virtual photons to give radiation. That's the first thing. So it sounded like you were saying you believe that there's this scalar virtual photon that is getting radiated out. I see two issues with that. The first being, first of all, the scalar mode in QED is not physical. Second of all, so you could say maybe there's some virtual stuff going on in that, but the virtual particles typically refer to internal lines, whereas in the Feynman diagrams, whereas the radiation are the external lines. So you can't have a virtual radiation mode in QED. So that seems to be
so what is
an
it
issue.
then? What is the equivalent, I guess?
I'm not exactly
when it's not
sure.
Closed.
I don't know what's going on. I don't know the best way to describe your experiment, if that's what you're getting at.
No, I'm just trying to figure out, how would you draw the Feynman diagram for just a point charge and its field? Not the self-energy, but just the regular.
Well, yeah. So if you think about what the electric field is, it's the force that you would get if you had a test charge located there. So you could imagine, exactly as you're saying, it's a 4-point tree-level scattering Feynman diagram where you have 2 electrons going in, 2 electrons going out, and you could have. It's a little subtle here because it's a classical phenomenon, but there is that internal line. And at first it becomes virtual, meaning it can have complex momentum that's off shell, but there's also momentum conservation, as you were saying. So that when you do that Feynman diagram and you're integrating over the momentum, you get this delta function from momentum conservation, and that basically conserves momentum such that you get classical momentum that can be transferred from one electron to another, and then they can get forced apart. And it's worth mentioning, you can also find the electric field in classical electrodynamics for as many charges as you want. Maybe I misheard you, but it sounded like you were saying you can't study things classically for 3 charges or something, but
well,
certainly
not
can.
multiplied together. I think the superposition is an addition of all the charges.
I also noticed, so you mentioned that you're doing time-independent perturbation theory, which I didn't pick that up. So perturbation theory, mathematically, it's kind of like a Taylor expansion. So the basic idea is you can have polynomials. So you could have, a constant term, then a linear term, and then a quadratic term. And the idea is if you're doing an approximation, hopefully the thing is small, so the higher order terms can be neglected. And then so perturbation theory is this approximation scheme that you can use to find solutions to things. And there's different ways you can apply perturbation theory in physics. Typically, when you refer to perturbation theory in quantum electrodynamics, it's not about time independence. It's more about when you write down the Feynman diagrams, you can have what they call tree level diagrams and then loop level diagrams. Typically, the tree level diagrams correspond to the classical interactions, and the number of loops in the diagram is the level of perturbation theory you're at. So the language that I'm familiar with is you'd have the classical theory is essentially the 0th order term, and you can think of it as a perturbation in H bar because H bar is small. That's a kind of way to colloquially think of it. Mm-hmm. And so you could have a 1-loop diagram that would be a first order correction, a 2-loop diagram, second order, so on and so forth. However, in quantum mechanics, before getting into quantum field theory, I'm pretty sure that you could do time independent perturbation theory. For what you're working with, you have a lot of DC. It's DC, so there's no time dependence, right? And so you could look at the frequency and you could say, well, it's a really long wavelength excitation. So I'm actually, I'll have to think more about what exactly you are doing, because I just assumed that you were doing the typical perturbation theory of quantum field theory, but now you're mentioning time independent perturbation theory. So
yeah,
I've seen some of your notes. Obviously, you haven't published something yet, so I haven't. I looked through what you were able to send me, but I'm just realizing now that you mentioned time independent perturbation theory, which wasn't what I was thinking. So maybe that it's worth disentangling. It's not saying you necessarily have an error there, but I'm just realizing that now.
No, I haven't done QED in 26 years.
Yeah.
So could use a refresher.
Yeah.
But I was just intrigued by just doing the time independent perturbation theory and getting something. I love your help translating some of that. The vertices that don't end. I understand these particles they're not real, right? You can't capture them. But I pictured them more like electric fields, where you can't pull the field from the charge, right? Have you now, field line? It doesn't work that way. And that's what these things, I think, represent. So that's why we have things like renormalization, these really complicated tools to try to address these infinities. A lot of infinities here. And that is a nasty integral that I have not been able to solve.
Yeah.
I'm only looking at the cartoon picture, trying to interpret it. But if you want to help me with that, that'd be awesome. With the real math, I had 5 or 6 kids started work on that. Gamma functions, error functions. These are not fun things.
Yeah, the integrals are definitely hard.
They are not hard.
Honestly,
it's not a beautiful solution like Coulomb's law. It's different.
Does the fact that Charles is talking about a time independent perturbation, which you kind of hadn't anticipated before the conversation, did that change anything as far as the viability in your mind with QED, or is that something you have to kind of think about offline?
You could do perturbations with frequency at the classical level. So if you're claiming it's a quantum effect, at some point, with the Feynman diagrams that you would have, would there be any loops in the diagrams that you've been studying?
Well, the zero orders are there, right? The non, where they start and the end. Yeah.
Also, I noticed
the self energy you're talking about. Yeah.
Yeah, there's
self energy terms. There's 12 terms, and I think half of them are not very useful, but maybe the other half are. That's what I'm proposing. Maybe they're interesting because they don't close in like you would want them to. You can't make the picture nice and neat in your head. And so this is a game, and I love this game because it's like try to use your mind, and our brains are not good at this. If I take 2 charges, we know they can attract and we know they can repel. But if you didn't see this one, and you see this one go there, your brain would say, well, I can't do that. Or if I take 2 charges and I stick them on a box, don't let them touch. Take the electrodes away. Are they still attracting? Damn right they are. For how long? Forever. So that is a fundamental property of charge fields, which QD, I think, explains quite well. So, but is it conserving energy? That's what you have to think about. Is it conserving energy? Still, you've removed all your energy to get that there. Why is it still there? So there's a little mind games with this, I think. Kind of helps. I think this Exodus is kind of here's another mind game for you.
I mean, it is hard to imagine what is going on there. I have to experimentally. I don't know what's going on. But it's curious because we have Noether's theorem, which describes energy momentum conservation from space-time translation symmetry, and Noether was actually studying quantum field theory and discovered something profound about classical mechanics, about the conservation laws. But even still, things are conserved off shell, so it's hard to, right, as you're saying, I mean, maybe there's some charges that we're overlooking, right? But they're honestly, it's at the point where if it appeared as if momentum conservation was violated, then you would claim that there's something else there that we don't understand, right? There must be something carrying that momentum.
Yeah.
I mean, that's how the neutrino was discovered. Initially, they had these decay channels, and they were counting the energy. They were accounting for the energy. And it's like, wait a second, the bookkeeping isn't adding up.
Yeah.
And then, isn't that how science kind of moves forward in some ways? I guess if you were to take your physics hat off and just as a human being look at all of the kind of overwhelming anecdotal evidence, because I know you've kind of systematically surveyed a lot of these like weird fringe experiments and exotic propulsion, free energy, all sorts of things like that. And to me, without any sort of physics background, I think you almost have to be dogmatic to say that there isn't some sort of there specifically around the lineage of the type of stuff that Charles is discussing. I don't know what you would say there. What do you think? Because clearly that is a way often that science moves forward. If you look at Thomas Kuhn in the structure of scientific revolutions, it's this like anomaly buildup, and then that sort of breaks the dam, and then the theory often is playing catch up on the anomaly.
Yeah, definitely. It can go both ways as well. But I mean, certainly out of all of these weird phenomena that seem to not fit into conventional theory, I mean, I would say your experimental results are, got to be in the top 10 in terms of most convincing things I've seen. I mean, there's other groups where they do one experiment and they're measuring piconewton forces, right? We've all heard these stories, and then people get in debates. Oh, is it some experimental error? Mm-hmm. Obviously, as you point out, you're not 100% sure. There could be some prosaic explanation, but the fact that you've done so many different things and you're seeing the self-consistency, I mean, even as a scientist, I have to say that is encouraging, and we should explore this further. It's not something we should just sweep under the rug and forget about.
What would be your best way? Obviously you haven't like rigorously kind of studied the experiment itself. You haven't been like on site with them, but would you have any way of explaining it away? Like if he is controlling for and eliminating this ion wind effect and actually showing that in a vacuum chamber you get more thrust, that to me that feels like pretty convincing. And then obviously this is being done in a Faraday cage, so there's no electric field interference. Is there any way that you could kind of poke at it or kind of straw man it from afar?
Honestly, no. And I've interacted with Drew multiple times on APEC with Tim Ventura. I've had private communications with him. I've interacted with him publicly. I've seen his iteration rate, first of all, is phenomenal, right? He's just always testing new things, trying different stacks with different materials and different geometries, and he's really dialing it in. It's really impressive, the innovation rate that he's going at, and your whole team. And so, I mean, if you've checked all these things that you say you've checked, right? I obviously I haven't been in the lab with you, but I can't think of anything, to be honest. I can't think of any prosaic explanation. I mean, if you're right, there's not much magnetic stuff going on. There's a lot of electrostatics, right? Not much charge moving. It's just so mind blowing, though. I mean, the idea that the claim is you power it up and then you unplug it from the wall and then the thrust continues in indefinitely, well, obviously you haven't tested it for an infinite amount of time. Drew would sometimes act as if it would last forever. I mean, my skeptical brain is saying, well, eventually wouldn't that capacitor discharge? Yeah. But still, even if it lasts a day, it seems like it lasts longer than a day from what you guys have done, as far as I can tell, in terms of the claims. It's hard to imagine how could that be continued? Like the fact that it's not getting drained, you would think, okay, well, wouldn't it require energy to get that thrust? Wouldn't that quickly drain the capacitor? It doesn't seem to be what you're claiming.
Yeah, that's
You've tested it in so many different ways that it's a tough challenge for anyone to try to describe what's going on there. It's very mysterious.
You're also friends with and looked at the experiments done by Falcon Space in this sort of area, in this sort of electrogravitic or maybe, new electrostatic force area. And they basically tried to pull off the Byfield-Brown effect. What was your take on that experiment?
Yeah, so it was actually interesting. It was curious. So it's not scientifically conclusive. Not all the experimental errors ruled out, but there was something interesting that was seen where they did the tests at not too low pressure and they noticed it spinning in one direction. And then eventually they kept pumping down further and further. And eventually it started spinning in the other direction, which it's, qualitative. We don't know how strong the force is. I don't know what the friction was. They had a nice mechanism to hold it up so it minimized the friction using magnets, which introduces additional potential errors, but I'm not too worried about the magnets. But if you're going to do a demonstration for others that are skeptical, you should probably maybe think to do it another way. So I think it was interesting and it was worth further study. It's suggestive, but not conclusive, I would say, where more work is needed.
Because of the magnets, or what
well,
would
no,
be the...
honestly, so there was this other thing where the way the high voltage was delivered to the thrusters on one end, it used the spiraling around the chamber. I mean, that's something you could point at and say, let's just say it's that. Honestly, I doubt it would be causing what was seen, but, it's something to consider. Really, to get a confirmed thing, it's best to do multiple tests, right? Not just one, and do it in different ways. But really, another issue potentially was the fact that there were these discharges that were observed. And Tim Ventura was actually one of the first to kind of get a little skeptical to some degree, because he had worked with those ion lifters back in the day with the triangular ones and the tinfoil. And so he had worked with high voltage and he was aware, because it took me time to realize this. You would think naively, well, okay, there's all this ion wind stuff, and that's because you're ionizing the air. So you just remove the air and do it in vacuum and I'm good, right? No ion wind to worry about. But what if there's ions or electrons literally flying off the thruster itself? Or what if the wires connecting them, we could see different discharges that were occurring. So what if you're spraying out these ions? What if that's causing the force? So it's something that it's also amazing to look into it. It's, first of all, it's a challenge enough just to work with high vacuum systems. Then it's another challenge. I mean, you're well aware of this stuff, to work with high voltage.
Sure.
But then to combine the two, it's remarkable.
Because you definitely want to enclose everything with you can. When I saw Mark's video, I was worried about the coil, because that would be, dubious. Why do you have a ground there? But it's not a ground, I guess, it's the high voltage wire. But it's interesting that it went one way, like you would expect. If it was a corona wind and then you pump it down, it goes the other way. That's cool to see.
Yeah. So,
but you don't, like you say, you don't want the discharges. You don't want the current coming off, even under high vacuum. You'll get field emission, it's called.
Yeah.
From materials. So you want to kind of make sure you encapsulate everything. So that would be the only thing that might be a hiccup, is the possibility of field emission. But I have not seen the experiment, but that's easy to prevent. You can corona dope it. You can do all kinds of things to kind of prevent that, encapsulate it. But yeah.
So I found it encouraging, but you got to keep studying further. I think, to really get to the bottom of it.
Well, on that note, I know we went deep into all sorts of, out there theories. But this was super, super helpful. And if you were to give Charles any advice as far as kind of fleshing out his theory or, places to look, what would it be?
Well, I would say, yeah. So if you're doing it, you could consider two different types of perturbation theory at the same time. So you can do the time independent one, and you can do the H-bar, the quantum corrections as well. So you could keep track of both of those. It's a little more complicated. You might not even need the time independent assumption, but since you're working with electrostatics, I also see why you're doing that. So it could make sense to do that approximation because it would simplify things, but then you just got to be, if it's truly DC, it probably would be a good approximation to do. So I think that would be one thing to do. Just, look into renormalization, the self-energy. Those perturbative corrections can affect the electron self-energy. Also, this is a puzzling thing. If you look at the Dirac spinner, which is used for electron in quantum electrodynamics, the spinner field, those equations of you can still have classical equations of motion for a quantum field, and those equations might have E or H bar or C. So you can get alpha in classical equations, but it's subtle because it's a quantum field theory, but there's a classical limit there. So I would say I honestly just try to learn as much as you can. Keep trying to, we can correspond via email and try to talk more about quantum electrodynamics, and we'll see. Maybe something more is needed, but I think it's a good effort to at least see where does quantum electrodynamics take you.
Sure.
But also just recognize it is a possibility that the results you're finding can't be described by quantum electrodynamics. Just keep that in mind.
Yeah. The reason why we like to use the QED, we haven't mentioned it much, but because of the alpha that shows up experimentally, that's really cool. Some of the fine structures, showing up in terms of the forces, and fine structure constant squared. So it's always some kind of function of alpha keeps showing up experimentally. There's not too many experiments you could do in your garage to get you an alpha.
And that points towards quantum electrodynamics.
It points to quantum.
Quantum in general.
I would say. No one knows where alpha comes from. I don't think anyone has a clue, but it's there.
Why does the fact that a fine structure constant is showing up point towards quantum mechanical effect?
That's a good question.
So
it's the coupling between fields and charge is what alpha is.
Okay.
So it's not too surprising.
So it's like a primitive in quantum mechanics, and that keeps showing up
in physics in general, and it shows up all over the place.
Yeah.
There's also another way to look at it where you can kind of look at it from a natural units perspective and just kind of set H bar and C to 1. I know a lot of people might not like that.
No, I don't like that.
Sorry?
I don't like that.
Yeah, I can understand why. I get what you're saying, but at the end of the day, alpha is proportional to, was it E squared? And the interaction term between the electron and the photon introduces a factor of alpha. So once you have that Feynman vertex where you have an electron, positron, and a photon, there's like a factor of alpha there.
Yeah.
And so if you're going to build these loop order corrections, you're going to need more vertices. So you will require more factors of alpha as you go out in the quantum perturbation theory. However, just remember that even for the Coulomb force, where it's a tree diagram, no loops, there's still, you could do a unitarity cut on that photon internal line, and there's still two interaction vertices, alpha and alpha, that get multiplied together, even for a classical process. So certainly tracking powers of alpha is helpful in perturbation theory, but just keep in mind that it comes in at the classical level as well.
That's exciting, yeah. Because I've been deriving the orders of magnitude between third order, I think, I didn't go to fourth order, but I actually did fourth order, third order, second order, first order, and you could see the perturbations in alpha. Alpha is nice to use because it's dimensionless.
Yeah.
It's the ratio of the energy of two charges divided by a photon of that same wavelength of where how far apart those two charges are. So that's what alpha is. It's the ratio of two energies. That's the best way to describe the Sommerfeld constant. So,
there was something else I want to mention you too. You had mentioned the term hidden momentum. So I believe there is work, certainly by the 1980s, where because in classical electrodynamics, the Poynting vector is what carries the momentum density, and that is proportional to E cross B. And so there were experiments where part of the reason why hidden momentum was found was in statics as well, where they had an electric field that was static and a magnetic field that was static, and they're perpendicular, so you get this E cross B. And it was puzzling because you would have a Poynting vector implying there's momentum, but I mean, I'm pretty sure if you just take a symmetric capacitor with an electric field going through and then you put it inside a solenoid with a magnetic field perpendicular, nothing's going to thrust, right? And the hidden momentum is what describes what cancels out so that you don't get thrust in those experiments. So that's just another thing to look into.
Well, that's where I started, right? So I started looking at field momentum being converted into linear momentum. And the crux was this 1970s hidden momentum, which is a relativistic effect. So even if you have a magnetic field, a current, you can always draw that as a kind of a square. And whenever there's the Faraday field, it will accelerate charges in one loop and decelerate them in the other loop. So it's basically a kind of a change of momentum physically of the loop of the electrons hitting the walls. That's how they describe the hidden momentum. So every time you have a static E cross B, nothing moved. Like you have a highly charged electric charge to a bar magnet doesn't fly across the room because of the hidden momentum. So that can be scaled down microscopically. So even the magnetic moments can be pictured as little currents. And they have hidden momentum because they're relativistic. So I first started out I started out in the 2000s to look at maybe the conversion from field momentum to mechanical momentum could happen like it does in the angular case, but for linear momentum, if there's no hidden momentum. So what's the opposite of relativistic charges moving? Electrostatics. Keep the charges static. Do static charges possess hidden momentum? And that's my theory was it didn't. So that led me down to that path where in 2010 I saw the forces initially. Could have been something else, but that's where I started. And it wasn't until after 2 years working with Drew, I said, "Oh, he's got the conversion down from field momentum to mechanical momentum without static charges." My wife pointed that out, and so we did the test. And so for 2 years, we thought that's what the case. It wasn't until 2018 where I realized that I didn't even need the current. So I'm not even setting up the E cross B fields anymore. So there's two electric fields and one magnetic field for that all to work. You have the E cross B, and then you kill the B to make a second E field called the Faraday's law field to convert it into mechanical momentum. But if you don't have hidden momentum, you should see thrust. So that's what we thought we were seeing until I realized just before going on a trip that I didn't even need a B field or a current. So, oh man, I'm in pure electrostatics mode.
Whoa.
So I don't have any field momentum, which was good and bad. It led us down this path.
Yeah.
So now we'll have to study that first before going back to that, which is far more complicated.
Super fascinating. Well, this has been a really fun discussion. David, thank you so much for lending your expertise here and for, talking to Charles in a way that's clearly like not dogmatic about the experimental results and then kind of helping sharpen his blade on the quantum electrodynamics. So really appreciate you both.
Thank you.
Thanks for having us, and it was a pleasure meeting you.
It was a pleasure meeting you too. Thank you.